Yeah, hi everyone. Welcome to the second part of transmission line. I hope you have already seen the first part. So even if you haven't studied EMFT, you don't know anything about EMFT, still you can watch this video. This particular video first you need to watch, then you need to watch this video, standing wave pattern on transmission line. So both are very important. If you even if you don't have any idea, still you can watch it. Now this standing wave pattern, this is one of the topic. Even if you are comfortable with EMFT, still you might be facing problem in this particular topic. But after this particular video, you will have a very clear idea that how to attempt particular questions from this particular topic. Okay, so let's get started. So first you need to watch this video, then only you should come here, right? So yeah, let's get started now. So here we are going to study about standing wave pattern. So first we need to study what do we mean by standing wave. Here we are going to see the problem solving technique only, but first we need to study what do we mean by standing wave. So there are two terms, traveling wave and standing wave. So both seems like the same thing only, but this is a picture at a certain time. This is a picture of a wave at a certain time. But what do I mean by traveling wave? That means if I click on the time button, then this wave will start traveling. It is traveling. Let's just say I call this axis as z axis. I am calling this axis as z axis. So now this wave is traveling in positive z axis, right? So this is a traveling wave. What do you mean by standing wave? So this is a picture at a certain time. But now if I click on the time button, what is happening here? If you clearly observe what is happening. So you will see one thing, that this particular node, just keep your eyes on these nodes. Okay, keep your eyes on these nodes. Keep your eyes on these nodes. Now what will happen? These nodes will be staying at their own point. These nodes will be staying at their own point. This node will also stay at their own point. So first let's see these nodes. These three red nodes that I have marked. Okay. So you see the wave is going up and down, but these are at their same point. Wave is going up and down, but these red, this one and this one, these are at their same point. Again, going up and down, but they are at the same point. Now let's see these peaks. Which peaks I am talking about? These guys. Now let's see these green dots now. Now what will happen? These peaks will move up, down, up, down, up, down, up, down, up, down, up, down, up, down. In that manner it will move. Okay, let's see it. Up, down, up, down, up, down. So this is known as standing wave. So this wave is standing at that own point only. That's why we call it standing wave. It is standing. But this is your traveling wave. This is your traveling wave. Have you done the string experiment? Like at 2 volts you can, like there is one guy standing in front of you, and you are standing here. You take a rope and you give a pulse in that particular rope. Like you give a pulse in that particular rope, then what will happen? That pulse will travel and then it will come back. So after that it will feel like that after some time that it is standing only. You might have observed standing wave in real life as well, but even if you haven't observed, then still you can see here. The traveling wave feels like that it is traveling in a particular direction, but standing wave is standing at their own point. It is going up, down, up, down, up, down. But what did you notice here? That these points are fixed. These are at their own point only. This point did not even move. Only the green points are moving. Now, if I ask you one thing, just a second. Yeah. If I ask you one thing, will you call this point as minima and this point as maxima? What I am asking, will you count this point as minima and this point as maxima? If someone says yes sir, this is the minimum magnitude, this is the maximum magnitude, so this is my minima and this is my maxima. But after some time what will happen? After some time this point is going to maxima and this point is going to minima. Let's just say I say that this distance is, let's just say, lambda by 2. So can I say at lambda by 2 I am having maxima? Sometimes it will be maxima, sometimes it will be minima. Right? So I know that this point is toggling. But I know one more thing, that this point is going to peak. What I am saying, that here you can either have the positive maximum or you can have the negative maximum. Same goes for this point as well. Either you will have the negative maximum or you will have the positive maximum. But these points are fixed at 0 only. Let's just say this is plus 5 volt, this is minus 5 volt. So sometimes it can have plus 5, sometimes it can have minus 5, sometimes it can have in between values as well. But these points will always be at point 0 only. So these points are known as minima. Are you getting this point? Which points are known as minima? This point, and this point. These are your minima. And this point here and here. Let me make it again clear. Okay. So this is the cycle. So this point and this point, these are known as maxima. So is that clear? Like in this chapter, we will study that what is the location of voltage maxima, current maxima, voltage minima, current minima. So is that clear that what do you mean by maxima? What do you mean by minima? Now, how do we show a particular standing wave? How do we show a particular standing wave? Okay, forget about it. We will talk about how do we show standing wave, but how standing wave is generated, that is the more important part. How traveling wave is generated? So any wave that you see, that is a traveling wave only. Light wave, it is a traveling wave. EM wave, in this chapter we study about EM wave. So EM wave is also a traveling wave. That means wave energy of the wave will travel. Here energy of the wave is traveling. Let's just see at this peak. So this peak will keep on moving. Just keep your eyes on this particular peak. This peak will keep on moving in that manner. So actually peak is not moving, the energy is moving. So you will see that the energy will keep on moving. Look, this peak is moving ahead, right? It is following the green path. So energy will keep on moving like that. So this is a traveling wave. So this traveling wave we can call it as forward traveling wave, because this wave is traveling in this direction. This wave is traveling in this direction. Now let's just say there is some boundary. Here there is some boundary. So assume my hand as a boundary. So a wave was coming like this. Now when it strikes the boundary, what will happen? It will be reflected back. Some part will be transmitted, some part will be transmitted, but some part will be reflected back. So this particular wave is traveling in this direction, right? This particular wave is traveling in this direction. Now this wave will travel in this direction. So one wave was coming like this, then some part was transmitted, some part will be reflected back. Now both combined, this was the forward traveling wave, this is the backward traveling wave. So forward traveling wave and backward traveling wave both combined will make the standing wave. Combined means superposition. So this is how you get a standing wave. So while going deeper into the chapter, first you need to know that how standing waves are generated, because people just study it, they don't even know how it is generated. That's why the topic become complex for them. Are you getting this point? There is a boundary, came, reflected back. Both combined are making standing wave pattern. Well and good. So this is how we get the standing wave. Now how we can show the standing wave? How do we show the traveling wave? We show the traveling wave in this manner only. In this manner only we show that, and then we say that this is a picture at a certain time. When we click on the time button, this energy will start moving. But how do we show a standing wave? Because the point here is that sometimes this is at negative peak, sometimes it will be at positive peak, sometimes this is at positive peak, sometimes this will be at negative peak. So how do we show it? We generally show the magnitude. So generally what do we do is that this is how we show it. Let's just say this point is this point. Here, this point I am showing like this. Are you getting this point? What I am saying, let's just say this is your y equals to 0 and this is your y equals to L. This is your y equals to 0. So this I am calling as y equals to 0 and this will be my y equals to L. So here how much magnitude I am having? 0. This will be at 0. After some time here also I will have a 0. After some time again I will have a 0. Right? At y equals to L again I am having a 0. And let's just say it is somewhere in between. So 0, then again 0 and then again 0. Okay for you? Okay. Now I know that this can go to the negative peak as well and this can go to the positive peak as well. So here I will show you the magnitude only. So this will be the magnitude of this pulse. Right? Same goes for this one as well. So this will be the magnitude. So the point is between two minima, there will be one maxima. I will only show the magnitude. Between two minima, there will be one maxima. That's why the waveform should be made like this. That means there should be like it should not come something like this. In a lot of textbook as well, and even in the gate examination as well, you will see this kind of waveform. But what we are doing, we are showing the magnitude, right? We are showing the magnitude. So here it is not differentiable. On this particular point, it is not differentiable. What if I tell you to draw the graph of sine omega t? So that will go like this. So there is a smooth transition, right? But if what if I show you, I tell you to draw the graph of mode of sine omega t? So it will go like this and then directly like this. So there is no smooth transition. It is not differentiable at this point. No. Before this point, the slope is negative. After this point, the slope is positive. So it is not differentiable at this point. So usually the standing wave pattern is shown like this. There should not be any sharp turn. The turn should not be sharp. It will be sudden. The turn will be sudden. It comes here, then it should be going like this. But even in the examination, if you see the standing wave pattern made like this, somewhat like this, then also you should not be confused. Okay. In the examination, sometimes the standing wave pattern can be made somewhat like this. They can make the standing wave pattern. Let's just say initially here we are having minima, but it's not necessary that always you will have a minima here. Let's just say initially you are having maxima. So in the examination, they can make the waveform like this as well. They will say that this is maxima, this is minima, this is maxima, this is minima, this is maxima, this is minima. But actually this is not the correct way. This is the correct way of showing it. Okay. The correct way would have been maxima, minima, maxima, minima, maxima, minima, maxima, minima. But even if you get the waveform in this manner, then also you should not be getting confused. So this is the concept of our standing wave. I hope you would have understood what do we mean by standing wave, what do we mean by traveling wave, and yeah, now we are going to relate it with our chapter. We did not start our chapter as of now. So now we are going to relate it with our chapter. So first you should know what is a transmission line, that we have already seen in our previous video. So transmission line is nothing but two wires. Transmission line is nothing but two wires. At the load of the wire, we will connect a load resistance. And at the source of the wire, we will give a supply. This is what we do in network analysis as well. Here we are doing the same thing. Here we are giving this supply. So what I am saying is that this supply will have a particular frequency, right? The supply will have a particular frequency. What do I mean by that? The input would be Vm sine 20 pi t. So what is the value of omega? 20 pi. What will be the value of f? 10. So this is what f I have written. Understood? So we are giving a supply which is having a particular frequency. If you know the value of f, can you let me know the value of lambda? Yes. What is the value of lambda? Vp by f. So let's just say this medium is having a permittivity of epsilon r. This medium is having a permittivity of epsilon r. If you have watched the previous video, then you will be able to relate what I am saying. If this medium is having a permittivity of epsilon r, then what will be the value of Vp? C upon under root epsilon r. And then f will be given. So can you find the value of lambda? Yes. So if there is f, that means certainly there will be associated lambda as well. If there is lambda, then can you let me know the value of beta? Yes. 2 pi by lambda. Right? So if there is lambda, then there will be beta as well. So all these parameters will be used in your analysis. Okay. So I am just writing down the formula. The formula are lambda equals to Vp by f. Okay. And beta equals to 2 pi by lambda. And Vp is equals to C upon under root epsilon r. So only these formula I am asking you to keep in your mind. And those you already might be knowing from your higher secondary classes. Right. Now, what will happen here? How standing wave patterns are observed on transmission line? Why standing wave pattern will be observed on transmission line? So let's get started with that. So what will happen? Just as I close this switch, so here a voltage wave will be generated. Just as I close the switch, a voltage wave will be generated. Now this voltage wave will travel. It is traveling. It will be a traveling voltage wave. It is traveling. Now what will happen? It will strike to this load. The voltage, just as you close the switch, the voltage wave is generated, that is traveling. Now that traveling voltage wave will strike to the load. What load will do? Some power it will observe. Some power load will observe. So this is how I am showing the observed power. Some power load will observe, and some power it will reflect back. So wave came, some power load have taken, and some power is reflected back. Some power is reflected back. Some power will be reflected back. and these two superimposed, forward traveling wave and backward traveling wave, these two superimposed will make a standing wave. So this is how standing wave pattern is observed on transmission line. Now what kind of questions will be asked? That on transmission line at y equals to 0 and at y equals to L, or in between anywhere, what will be the location of voltage maxima, what will be the location of voltage minima, how many maxima will be observed, how many minima will be observed, what will be the maximum value of resistance, all these kind of questions will be asked. So those questions we are certainly going to see. So now you are able to relate what we are going to study in this particular chapter. Now you are able to relate why we studied all these things, right? All clear? Now what did I say? That some power will be coming into and some power will be reflected back. So before power, let's talk about the voltage magnitude. So let's just say the incident voltage was V0 plus and reflected voltage is V0 minus. So the ratio of reflected voltage to the incident voltage is given by a particular expression. What I am saying, y equals to 0. What I am saying, there is a particular expression that is defined, that is known as gamma L. What is this? This is your reflection coefficient at load. Reflection coefficient at load. And what is the value of reflection coefficient at load? That is ZL minus Z0 upon ZL plus Z0. Will that be easy for you to remember? ZL minus Z0 upon ZL plus Z0. A very important formula. If you don't remember it, then your things will not work. Only this formula you need to remember. ZL minus Z0 upon ZL plus Z0. Reflection coefficient at load. Very, very important. And the important line is this. This is reflection coefficient at load. That means this is the reflection coefficient at y equals to 0. Reflection coefficient will change with respect to y. Everything changes with respect to y. Do you remember? Z of y. So at load, the impedance was ZL. But when you walk into the transmission line, the impedance was getting changed. Same goes here. The reflection coefficient at load is ZL minus Z0 upon ZL plus Z0. But when you walk along the transmission line, the reflection coefficient will be getting changed. And what do you mean by reflection coefficient? The magnitude of reflected voltage, ratio of magnitude of reflected voltage to the incident voltage. This is your reflection coefficient. And this formula I have written, reflection coefficient at load. And what we are talking about? We are talking about voltage. So this is the reflection coefficient at load for voltage V. Okay, reflection coefficient at load for voltage V. For voltage we are talking about. We will talk about current as well, but first let's talk about voltage. And how standing waves are shown that I have already told here. Okay, so here I am not gonna write down how standing waves are shown. So this is how the standing waves are shown. Okay, so again I am not going to write down the same thing. So let's just remove it off. So from this slide, what all things you need to remember? There will be a transmission line, there will be a load. I will give a supply. It will have a frequency. It will have a particular frequency. If frequency is there, that means there will be lambda. If lambda is there, that means there will be beta. There will be a load. Just as you close the switch, voltage wave will be traveling. It will be reflected back. Both combined will make standing wave. Okay. The reflection coefficient at load is given by ZL minus Z0 upon ZL plus Z0. And that is the reflection coefficient at y equals to 0. Well and good. Okay. Now let's just solve a question. For a transmission line, Z0 value is given, ZL values are given. You need to find the value of a reflection coefficient at load. Then you need to plot it on gamma plane. What is this gamma plane? That I will tell you. Okay. And you will understand as well, on your own as well, you can understand. What do we mean by this gamma plane? You will understand, but let's get started. What we need to find? We need to find the reflection coefficient at load. At load. Again and again, I will say the same thing. This is the reflection coefficient at load. So first question, part A. Gamma L, reflection coefficient at load, and this is for voltage only. So formula is ZL minus Z0 upon ZL plus Z0. If you apply the formula for 3 times, you will be able to remember it. What is the value of ZL? 50 plus 50J. ZL minus Z0 upon ZL plus Z0. So 50J upon 100 plus 50J. That is J plus 2J. That is equals to 1 by under root 5. Let's write down the angle. Okay, let me do the calculation by pausing the video and then I will write down the angle. Yeah, so the angle is 63.43. I hope you know how to write down these angles, because if gate examination is 12 days apart and you don't even know how to write down these angles, then I don't think you should watch this video, right? I hope you know how to write down these angles. So this is the reflection coefficient at load. Okay. Now you need to plot this reflection coefficient on gamma plane. So basically, what is this reflection? This is a complex quantity, no? This reflection coefficient is a complex quantity. So I need to plot it on a complex plane. So gamma will have a real part as well, and gamma will have a imaginary part as well. So this is what I am doing. This is gamma real, and this is gamma imaginary. In which form I have written it? I have written it in polar form. So you know how to plot all these things in a plane, right? Let's just say this is a quantity 2 plus 3j. How will you plot it? We plot it in Argand plane. 2 plus 3j, 2 plus 3j. Here we will plot it. Or how you could have done? I would have found the magnitude. What will be the magnitude? 9 plus 4, 13. And then there will be some positive angle. So angle is always taken in anti-clockwise direction. So this will be the positive angle. So same thing I am going to do here. What is the magnitude? That is 1 by under root 5. So let's just say this shows my magnitude 1 by under root 5. And angle is positive. The angle is 63.43. So let's make it a bit better. Angle will be 63.43. So somewhat it is like this. So this will be 63.43. This angle. So this is the gamma L value. Magnitude is 1 by under root 5. So this is how I will show it in the gamma plane. Okay. So this is coming with respect to ZLA. Let's call it ZLA because this was option A, no? So I am calling it ZLA. So with respect to ZLA, this is my point. This is not the value of ZLA. But with respect to ZLA, this is the line I am getting. Are you getting this point? What do I mean by that? With respect to ZLA, this line I am getting. So this is how I will plot it on the complex gamma plane. Why we are doing so? All the points will be related. So just hold on to the video. Just watch the video with good amount of patience. You will understand everything. Why we are doing all these things. Okay. Let's go to the second question. Same, we need to apply the formula ZL minus Z naught upon ZL plus Z naught. So what will happen? You start doing the things on your own. Okay. Now you don't need to watch the complete solution. You can do it on your own. ZL minus Z naught upon ZL plus Z naught. I should have already done the calculation actually. Okay, I will pause the video and then do the calculation. Here, am I doing something wrong? ZL minus Z naught. Yeah, I forgot to. ZL minus Z naught. It will be minus 50J, no? Because my ZL is 50 minus 50J minus 50 minus 50J upon ZL plus Z naught. So 100 minus 50J. 100 minus 50J. So minus J. I will do this calculation. Yeah, so what you will get? The magnitude will be 1 by under root 5. And certainly the angle will be just negative of this one. That is this thing. Okay. So this is what you are getting for second question for option B. So can I plot it on complex gamma plane? Yes. So let's do it on the next page. Let's do it on the next page. I will plot all the points on complex gamma plane now. So our ZLA came somewhere here. ZLA, this was our ZLA, 63.43. Now ZLB will be making minus 63.43, right? This is your ZLA. This was your ZLA. This will be with respect to ZLB. The magnitude is same, 1 by under root 5, 1 by under root 5, but the angle is minus 63.43. Angle is minus 63.43. Both are two different questions, okay? But I am plotting it on one plane only, so that we can relate the things. Option C. ZL is 100. So what will be your gamma LV? ZL minus Z naught upon ZL plus Z naught. So what you are getting? 1 by 3. Angle 1 by 3. Angle is 0, right? So 1 by 3. 1 by 3 angle is 0. It will be plotted somewhere here, right? 1 by 3 angle is 0. So this is your ZLC. What about D? Gamma LV. 25. So ZL minus Z naught, 25 minus 50, 25 upon ZL plus Z naught, 75, minus 1 by 3. Minus 1 by 3 means angle is 180 degree, right? Can I write it down in this manner? 1 by 3 and angle is 180 degree. And what about the 180 degree angle? This is somewhere here. So this is my ZL, ZLD. ZL equals to 50. So this is the case of ZL equals to 50, that is equals to Z naught. So what will be your gamma L? ZL minus Z naught upon ZL plus Z naught. So what will be the answer? 0. So now are you able to understand why did we study impedance matching in the last lecture? Here we were studying impedance matching, stub matching and this impedance matching in the last lecture, and I told you our target should be to make ZL equals to Z naught. If I make ZL equals to Z naught, then my reflection coefficient will be equals to 0. If I make ZL equals to Z naught, then my reflection coefficient, this coefficient will be equals to 0. That means all the power that is coming here, all power will be absorbed by the load. So this is my target, no? Whatever the power that I am giving from here, my target is that my load should take all the power. No power should be reflected back. All the power should be taken by the load. So if I want the load to take all the power, I don't want any power to be reflected back. I want load to take the all power. Then my ZL should be equal to Z naught. So that's why we were studying impedance matching. Now this is clear to you. So what will be my reflection coefficient now? Reflection coefficient will be 0. 0 means here. EF. F is ZL equals to infinity, ZL equals to 0. Then ZL equals to infinity. So what is the reflection coefficient? ZL minus Z naught upon ZL plus Z naught. ZL is infinity. That means ZL is very larger than Z naught. So Z naught can be ignored. Here also Z naught can be ignored, right? ZL is infinity. That means ZL is very larger than Z naught. So what will be the answer? 1. So reflection coefficient is 1. Reflection coefficient is 1. So somewhere here, that will be my ZLF. EFG. ZL is equals to 0. That means what will be your reflection coefficient? ZL minus Z naught upon ZL plus Z naught. So what will be the answer? 0 minus Z naught upon 0 plus Z naught. So that will be minus 1. Minus 1 means 1 but with the angle of 180 degree. So this will be your ZLF. Why we are doing so? Just have the patience, you will understand. Okay. Don't like lose in between that, sir, why we are doing all these things. You will certainly understand. It will just make the problems very easy. Otherwise the problem on this what do we call it, this standing wave pattern, these problem become very complex if you don't have your concepts clear. Okay. EFG, there is no H here, there is no H, right? But let's build some H. EFGH. So let's take H as 50J. Yeah, EFGH I. Let's take I as minus 50J. Okay. So what will be your H? Reflection coefficient V. ZL minus Z naught upon 50J I have taken, yeah. No, 50 plus 50J I took, no. 50 plus 50J, yeah. ZL minus Z naught upon ZL plus Z naught. So magnitude I can see will be 1 only. J minus 1 upon J plus 1. So magnitude will be 1 only, there is no doubt. But what will be the angle? Minus 1 J. Minus 1 here, J here. So this angle will be 135 degree. Minus this angle will be what? This angle is 45 degree. So angle will be what? 90 degree. So for this case, angle will be 90 degree. Magnitude is 1, angle is 90 degree. This much like basic of mathematics you should know, because I cannot teach all this basic mathematics in these particular lecture. In comprehensive course, we certainly teach this mathematics, but here you should know this much of basic mathematics. So 1 at angle of 90 degree. 1 at angle of 90 degree. This will be your ZL H. Okay. EFG H I. What will be your ZL I? That is minus 50J. Minus 50J minus 50 upon minus 50J plus 50. So here also you can see that this angle minus J and minus 1. So this will be minus 135 and minus J plus 1. Minus J plus 1. That will be minus 45. So angle will be minus 90. So magnitude is 1. Angle will be minus 90. Okay. So this will be your ZL I. So from here, what do you see? What was this impedance? If my load was purely inductive, then it is coming on gamma imaginary axis, but on the positive part. Coming on gamma imaginary axis, but on the positive part. If my load is purely capacitive, then also it is coming on imaginary axis only, but on the negative part. What was this? This was complex load, but it was inductive. This was our first example. Complex load but inductive. So if it is complex but inductive, then it will come on the upper hand part, right? If it is a complex load but inductive, then it will come on the upper hand part. That means it will come here. But if it is a complex load but capacitive, then it will come on the downward part. Here on this part, resistive element came. Let's talk about ZLC. This was resistive. ZLC is resistive. This is also resistive. But here this ZL was greater than Z0. This is ZL less than Z0. So on the real axis, resistive part will come. But here the condition will be ZL greater than Z0. But here the condition would be ZL less than Z0. And it will be the resistive part. What it will be? It will be the resistive part. Now you will say that, sir, ZLF was infinity. So it can be neither, you cannot call it neither resistive, you cannot call it neither inductive, you cannot call it capacitive, you cannot call it complex, because it is infinity. So impedance is infinity. So if the impedance is infinity, then you can understand it as a resistive only. So certainly this is ZL is greater than Z0, no? Here ZL is greater than Z0. Certainly this is ZL less than Z0, right? And this is the condition of ZL equals to Z0. So what do you see here? This is your ZL equals to Z0. If you go to this side, that will be ZL greater than Z0. If you go to this side, that will be ZL less than Z0. Is it tough to remember? No. Because how do we show the inductive part? This is how we show the inductive part. How do we show the capacitive part? This is how we show the capacitive part. So here we show plus J. Here what do we see? Here what do we show? Plus J. Here what do we show? Minus J. So whenever there is a capacitive part, it will be coming downward. Whenever there is a inductive part, it will be coming upward. If it is purely inductive, that means it will be coming on imaginary axis only. And if it is resistive means, so if it is ZL greater than Z0, if value is higher, that means it will come on the positive side. If the value is lower, then it will come on the negative side. Is it tough to remember? No, it is not tough to remember. And again, a very important point, here we are not plotting the impedances. We did not plot the impedances. What did we plot? We plot the gamma L value. What we plot? We plotted the gamma L value. Again and again I will say the same thing. In the examination, you will plot the impedance. What you will say? Okay, my impedance is 50 plus 50J. Make the complex gamma plane. Okay, impedance, sorry. ZL is 50 plus 50J. Make the complex gamma plane and plot this 50 plus 50J. Magnitude will be 50 under root 2. Angle will be whatever you find. So impedance you don't need to plot. What I am plotting? I am plotting the value of gamma L. Because what plane it is? It is the plane of gamma. So what value you will plot? You will plot the value of gamma, no, not the impedance. So what we are plotting? We are plotting the impedances. So is the conclusion clear? That what is happening? Upper part will be inductive, downward part capacitive, resistive. ZL greater than Z0, ZL less than Z0, middle part ZL equals to Z0. If purely inductive, that means on imaginary axis positive part. Purely capacitive, on imaginary axis negative part. Well and good. Okay. These kind of questions can also be asked in the examination, and a lot of students fail in this kind of analysis. This is nothing but Smith chart. We are studying Smith chart, but I did not name the topic. If I name the topic that we are studying Smith chart, then you would have understood that Smith chart is very difficult. How we will understand? But without even taking the name of Smith here, all these analysis I did not do. Smith did. We are just understanding it. So without even taking his name, I am just telling you that how to study his particular chart. So we are studying Smith chart only here. Okay. Now we are going to see important things. Some important things regarding gamma plane. So first you need to see what kind of questions will be asked. So this kind of questions will be asked. That your Z0 will be 50 ohm. On a transmission line, your characteristic impedance is 50 ohm. Your ZL is 50 plus 50J. The load is 50 plus 50J. Standing wave pattern will be observed on the transmission line because there will be some reflections and both combined will make the standing wave. Then they will ask, find the distance from the load at which voltage maxima is occurring. That means this will be your y equals to 0 and this will be your y equals to complete length. So on the complete length, at which distance your voltage maxima will occur, or voltage minima will occur, or current maxima will occur, current minima will occur. You need to find the standing wave ratio. What is the standing wave ratio? We will talk about. And then these kind of questions. These are like very typical to solve, but we will develop good problem solving skills and you will have a very good aptitude to answer these kind of problems. Then they will ask, on transmission line, what is the maximum value of resistance and where it will occur, or what is the minimum value of resistance where it will occur, and at what distance from the load you will get the purely inductive impedance, and at what distance from the load you will get purely capacitive impedance, right? So how we will solve these kind of problems? So first what we are going to do, first we are going to find the value of gamma L. Then it will have a magnitude and it will have an angle. Okay, it will have an angle. So let's take this example only. Let's take this example only. With respect to the example, we can understand. So let's take the first example. So this is my load and this is my Z naught value. So what will be my value of gamma L? Gamma L at load. That will be ZL minus Z naught upon ZL plus Z naught. So ZL minus Z naught upon ZL plus Z naught. So we have already found it. What did we get? Arey yaar. So magnitude was 1 by under root 5. Angle was 63.43. So just as I have got this thing, I will plot it on our gamma plane. Okay, this is my gamma real and this is my gamma imaginary. So I will plot it on my gamma plane. So first what I'm gonna do, this is how I have plotted it. Magnitude is 1 by under root 5 and this is the angle. Now taking this as a radius, I will draw a circle. Taking this as a radius, I will draw a circle. Okay, just listen to my points very carefully and keep your full concentration high. Taking so taking this point at radius, I have drawn a full circle. So this is my point y equals to 0. That means I am at load. What I have plotted? I have plotted the reflection coefficient at load. What did I plot? Reflection coefficient at load. That means I am at y equals to 0. Now I will keep on walking. Here there is my transmission line. Here there is my transmission line. This is my transmission line. This is my y equals to 0 and this will be my y equals to L. So now I will keep on walking on this transmission line. So this circle is my transmission line. So how you need to walk? Either you can walk anti-clockwise as well and clockwise as well. So where you will walk? You will need to walk clockwise. I am writing down this point. Always walk clockwise. Okay? Because time is money. Time runs us. So we need to walk with respect to time. That means we always need to walk clockwise. So after drawing this circle, I will make this arrow. That means I will walk clockwise now. Okay. Now I am walking on transmission line. This is your y equals to 0. That means I have drawn my reflection coefficient at load. Then with respect to that, I have drawn the circle. So now, as of now, I am at this point and this point is my load. Right. Now if I start walking clockwise, so after some time I will reach here, then I will reach here, then I will reach at this part. If I keep on walking, I will reach at this part as well, then slowly here as well, and then I will come back. So if I come back here, I have started walking here, and if I have come back here, then what do you think how much distance I have covered? Use your brain and answer me. I started walking on circle and I came back. If I am walking on the circle, what does that mean? That I am going in this direction. On transmission line, I am going in this direction. So if I am starting and I have came back on the same point, that means how much distance I have covered. Think about it. The distance I have covered is lambda by 2. Why is that so? Because on transmission line, after every lambda by 2, the same things happen. Right? So if I have covered the complete thing, if you remember the ZY value, what did I tell you? After every lambda by 2, the same impedance is repeated. So here you were, and if you come back, that means the same impedance you have got. This distance could be lambda as well. This distance could be 3 lambda by 2 as well. This distance could be 2 lambda as well. It could be anything. So covering one complete circle, that means if you have walked for 360 degree, that means you have covered the distance of lambda by 2. So walking 360 degree on this particular circle is equivalent to walking lambda by 2 on transmission line from the load. Is that point clear? Very, very important point. Okay. You are studying one of the craziest thing of not even EMFT. You are studying one of the craziest thing of complete electronics, Smith chart. When you go to the masters, these things you will find very complex. So is that point clear? One by one we will go with like good amount of patience. We will go. I'm not in hurry anything, but I'm pretty sure this year the question is coming from this particular topic. That's why I thought of making this video. So have the patience. Did you understand this point? If I'm working on the Smith chart, not Smith chart, don't even take the name of Smith chart. If I am working on this circle for 360 degree, that means I have covered the distance of lambda by 2. So 360 degree is equivalent to lambda by 2. If I say I have worked for 90 degree, that means how much distance I would have covered? Lambda by 8, right? 1/4 of this one, lambda by 8. Basically, if I am working for 360 degree, that means I have covered the distance of lambda by 2. That means if I work for 1 degree, I would have covered the distance of lambda by 2 divided by 360, that means lambda by 720. And if I am working for 90 degree, that means I would have covered the distance of into 90, and that is equivalent to lambda by 8. Is that point clear? Okay. Now another thing. If you keep on working, and you reach here, you reach at this point, what do you think, what kind of point it will be? Resistive? Say yes or no. What did I tell you? On this particular axis, you get a resistive load. So this point will be resistive. What are you understanding? On a transmission line, this is my transmission line. On a transmission line, if I am standing here, that means my load is this thing. That is complex inductive. My load is complex inductive. Complex inductive. Now, when I walk on transmission line, what will happen? My impedance will change. This we have already studied in our previous chapter. Sorry, in previous video. That when you walk on the transmission line, your impedance will change. So now your impedance is changing. Here the impedance was like this, like this, like this, like this. When you reach at this point, your impedance became resistive. So it somewhere here, after covering this much of distance, after covering 63.43 degree, on transmission line, your impedance is becoming resistive. So this point will show the resistive. This point will show the resistive nature. And this is the point of voltage maxima. Can you remember this thing? Why maxima? Because towards this hand side, what we are getting? ZL greater than Z0. Here we plotted ZLC. What was ZLC? 100 ohm. So here you are getting R maximum. This is the point of R maximum, and this is the point of R minimum. So here you are getting the maximum value of resistance. And what is resistance? Resistance is voltage by current. So if it is maximum, that means here voltage is maximum and current is minimum. So this is the point of voltage maxima, current minima, and R maxima. Is it tough to remember? It might be tough to remember, but how you will remember it? So you just let me know. In the word, there are more righty or more lefty. You might be a lefty, you might be a righty as well, but in the word, there are more righty or more lefty. More righty, right? There are more righty. So in the word, there are more righty. When we started studying the transmission line, did we start with voltage or current? We started with voltage. When you study network analysis, how do we start? With voltage. When we study diode circuit, when we study analog electronics, how do we start? With voltage. Voltage, voltage, voltage. In whole electronics, we keep voltage at higher priority than current. I don't know why, but we keep voltage at higher priority than current, right? So who is my priority? Voltage. How many people are there which are righty? More people are there which are righty. So on right hand side, I will get voltage maxima. My priority is right hand side and voltage. So on right hand side, I will get voltage maxima. So what do you think, what will be this point? So this will be the point of voltage minima. If voltage is minimum, then current is maximum and resistance is minimum. Say yes or no. Are all these points clear to you or not? Are you having fun studying all these things? Like if you would have studied it in comprehensive course, those who have studied EMFT completely, and after gate examination they can come back and watch the video of Smith chart, or at least watch transmission line, because that will help you a lot in masters. So I have taught in that manner only, so that you don't find any difficulty in masters. So you can go and come back if you want to study it comprehensively. But as of now, you need to understand this much analysis, and believe me, you will be able to solve every single problem. The problem which are considered as the toughest problem of gate examination, those also you will be able to understand. And in this lecture only, those problems we are going to solve. So just have the patience and watch the video with good amount of patience, right? So what did we do? We started with plotting the impedance. Then we are working clockwise on this particular circle. And working clockwise means I am working from the load on transmission line. When I cleared the distance of this theta angle, I reached to this point. When I have reached to this point, that means this is my location of V maxima, I minima, and R maximum. And then I will again work. I will again keep on working, 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 and then I will reach at this point. So this will be the location of voltage minima, current maxima, and R minimum. Now let's just say I was at this point. At this point, I was getting my voltage maxima, right? So this was my transmission line. So let's just say I needed to walk x distance. I needed to walk x distance to get my voltage maxima. Okay. This is I am saying that from the load you needed to walk x distance. That means you needed to walk this theta angle. And what this theta angle will be equivalent to? This theta angle is equivalent to x distance. This is what I am saying. Then you answer me one thing. To reach from this voltage maxima till the voltage minima, how many distance I need to walk in terms of lambda? From this voltage maxima, if I need to reach to the voltage minima, then how much distance I need to walk? How much angle I need to walk from here to here? How much angle I need to walk? 180 degree, right? I need to walk 180 degree. 360 is equivalent to lambda by 2. 180 will be equivalent to lambda by 4. So that means this is your voltage maxima. If you need to go to voltage minima, so you need to cover a distance of lambda by 4. And is this thing related? Yes. Related to what? Impedances. So in the previous video, what did we study? That after every lambda by 4, the impedance will be inverted. Say yes or no. Are you getting this point? Are you able to relate the thing? Right? So after every lambda by 4, so this much distance in radian, this in the angle, this distance is 180 degree. But actually this distance is equivalent to lambda by 4. Right? And then from this point, if I come back to this point, again from voltage maxima, I am coming back to voltage maxima again. That means I have covered the total distance of lambda by 4 plus lambda by 4. That means I have covered the total distance of lambda by 2. So after every lambda by 2, the same thing will be repeated, and after every lambda by 4, there will be inversion. So let's just say I started with this particular point. I started from here. Then after a distance of x, what I am getting? Voltage maxima. Then after lambda by 4, I will get voltage minima. Then again after lambda by 4, I will get voltage maxima. Then minima. Then maxima. Then minima. Is your brain now getting these things? And you can believe me, this is the most complex thing you are understanding of whole electronics. And you are able to relate everything now. From last lecture point 1 to this point, you are able to relate every single thing. Right? So what if I ask you, what is the distance between two conjugative maxima? What is the distance between two conjugative maxima? What will you answer? Lambda by 2. What is the distance between a maxima and a minima? Lambda by 4. Right? And one more thing, wherever there is voltage maxima, there will be current minima, and whenever there is voltage minima, there will be current maxima. And similarly, there will be R minimum and R maximum. Okay? So all these are just points are related. We will solve a lot of problem, and you will build one good problem solving technique as well. Okay? Yeah. So now let's understand another thing. So there will be one term that will be known as standing wave ratio. What this is known as? Standing wave ratio. So sometimes they can ask you voltage standing wave ratio, or sometimes they can ask you current standing wave ratio. Voltage standing wave ratio, current standing wave ratio, both are the same thing and both are denoted by S. So there is a formula of that. What is the formula? 1 plus mode of gamma divided by 1 minus mode of gamma. Okay, standing wave ratio, this is the formula. What does it represent? This represents the Vmax divided by Vmin or Imax divided by Imin. What do I mean by that? When I make the standing wave pattern, when I make the standing wave pattern, so let's just say this is how I am getting the standing wave pattern. So what is this? This is my Vmax. And what is this? This is my Vmin. So the ratio of Vmax to Vmin is my standing wave ratio. So the formula is 1 plus gamma upon 1 minus gamma. Will you be able to remember it? Another formula. Two formula only I am asking you to remember. Right? ZL minus Z0 upon ZL plus Z0. 1 plus gamma L up, 1 plus mode of gamma L upon 1 minus mode of gamma L. So this quantity can never be complex. Standing wave ratio can never be complex because here you are putting the mode. Right? Well and good. So we will use this thing. We will use this thing somewhere. Now we will try to solve this problem. Here I will write down the point. Distance between two maximas, lambda by 2. Distance between two minimas, lambda by 4. This is the minimum distance. But other distance could also be there, no? Lambda, 3 lambda by, oh sorry, 2 minimas, really sorry, lambda by 2 only. Or 2 lambda anything. This is lambda, 3 lambda by 2, 2 lambda anything. Distance between a maxima and minima, conjugative maxima and minima, lambda by 4. This is the minimum distance, other can also be there because after every lambda by 2 the same thing will be repeated, right? So these points we have written. Let's start solving this problem. You will understand a lot of points. You might not be able to solve all these question in one go, but after that, after going through this whole analysis, you will understand every single thing regarding transmission line, regarding standing wave pattern on transmission line, and that is a very complex topic and a very important topic that we are going to cover. So let's get started. First, what we need to do, we need to make the same thing. What we will do, we will first we will get the value of reflection coefficient, that is 1 by under root 5 angle. So I will get that value and then I will draw a circle with respect to that. So how much is this angle now? 63.43 degree. And if someone asks me what is the magnitude of gamma, that is 1 by under root 5. Angle is this 63.43. So here you are at y equals to 0. Now what they are asking? First question, find the distance from load at which voltage maxima occur. So one thing I know that voltage maxima will be equals to current minima and voltage minima is equals to current maxima, right? So I am at y equals to 0. Where is the point of voltage maxima? This is the point of voltage maxima. Right hand side voltage. There are more IT and voltage is our priority. So this is the point of voltage maxima and this is the point of voltage minima. Don't think sir okay, resistance part, nothing like that. Just understand right hand side voltage maxima, left hand side voltage minima. That means this will be the point of current minima and R maxima. So this will be the point of current maxima and R minima, right? So you are at this point. Now you need to reach, how you will walk? Clockwise. Now you need to reach at this point. How much degree you need to walk? From here to, I need to reach to this point, 63.43 degree. How much degree I need to walk? 63.43 degree, right? 360 degree is equivalent to what? Lambda by 2. 1 degree is equivalent to what? Lambda by 720. 63.43 degree is equivalent to what? To this thing. So what will be the answer? 63.43 divided by 720. 63.43 divided by 720. So 0.088 lambda. 0.088 lambda. So this is the point of voltage maxima, current minima and R maxima. Now those who have already studied this topic, comment down in this video that how complex it was to calculate this value. Like people will mug up the formula. They will say that okay, n equals to positive, you need to put negative, you need to put that. Then they will check 2 beta, theta max. These kind of formula they remember. In the examination, first thing, it is very tough to recall those formula, and they will frame, if they frame a conceptual problem, then you will be messing up there in the examination. But if you solve by this method, then there is no chance you are going to mess up. Are you getting this point? So just if you walk 0.088 lambda distance from load, at that point you are going to get your voltage maxima. What will be the point of voltage minima? This will be the point of voltage minima, right? This is the point of voltage minima, current maxima and R minima. So what do you think where I will get my first voltage minima? Do I need to calculate? I can calculate with respect to angle as well. How much angle I need to work to reach this point? 180 degree plus 63.43 degree. How much angle I need to work? 180 degree plus 63.43 degree. When you solve it, what you are going to get? 243.43 degree. And that will be equivalent to what? Lambda by 720 into 243.43 degree. So this calculation you can do and you will get your answer. Or what you can do? That sir, this is the point of voltage maxima. Now I need to go to voltage minima, then I need to work another lambda by 4. If I need to reach at this particular point, then I need to work another lambda by 4. So this is my point of voltage minima, voltage maxima. So if I need to reach at voltage minima, then I need to work another 0.25 lambda, right? So what will be the point of voltage minima? So 0.088 lambda plus 0.25 lambda, right? So how will you make the standing wave pattern now? How will you make the standing wave pattern? Before making the standing wave pattern, first let's find the value of standing wave ratio. What that would be? Divided by 1 minus mod of gamma. So what is your mod of gamma? 1 plus 1 by under root 5 divided by 1 minus 1 by under root 5. So what you are getting? Under root 5 plus 1 divided by under root 5 minus 1. 5 under root 5 under root value. What is the value of 500? 2.236. 2.236 plus 1 divided by 2.236 minus 1. That is coming out to be 2.62. So this ratio is coming out to be 2.62. So this ratio is not infinity. Let's just say this is my, at y equals to 0. At y equals to 0, I am not getting any maxima. Neither I am getting minima. So I am somewhere in between. After that, what I will get? Maxima. Then what I will get? Minima. Then what I will get? Maxima. Then what I get? Minima. Then maxima. Then minima. In that manner I will go. But the minima will not be equals to 0. Why is that so? Because if minima was 0, so what is my S? That is V max divided by V min. If my S was infinity, let's just say S was infinity, or I say if my V minima was 0, then only I would have got S to be infinity, no? But I am getting S to be finite. That means my minima value is not equals to 0. Okay? Actually, the maximum value is always V0 plus, you don't need to remember it, okay? This is the maximum value and your minimum value is, this is your minimum value, but you don't need to remember it. You just remember the standing wave ratio. So what is this point? What is this point? So this point is y equals to 0.088 lambda. What is this point? This point is y equals to 0.088 lambda plus 0.25 lambda. What you are getting? 0.088 plus 0.25. So this point is 0.388 lambda. So that's about voltage. That's about voltage. But current will be opposite, no? What did I say? That's about voltage. Voltage maxima you are getting at 0.088. But what about current? If I draw the standing wave pattern of current. So for current, what will happen? First you will get minima. Where you are getting voltage maxima, there you will get minima. In that manner we will get for current as well. This is for what? current. So I'm not showing the locations and all these things, you can show it on your own, but I hope you would have got the point, right? So did you get the answer of first 4 questions? At what point voltage maxima will occur, at what point voltage minima will occur, at what point current maxima will occur, at what point current minima will occur. So let's write down here. At what point voltage maxima will occur? So voltage maxima will occur 0.088 lambda. What will be this point? Voltage maxima. What will be this point? So after every lambda by 2, the things will be repeated. After every lambda by 2, the things will be repeated. So 0.088 lambda, 0.088 lambda plus 0.5 lambda plus 0.088 lambda plus lambda. In that manner we will go. So this is the point of voltage maxima, or you can say current minima. So this is the answer of A and D, right? The answer of both of them is this. What about C and B? Both will have the same answer. So first we will get started with where we are having the minima. So 0.388 lambda. This is the point of minima. After that 0.388 lambda plus 0.5 lambda. 0.388 lambda plus lambda. In that manner we will go. Okay. So this is the answer of ABCD. What next they are asking? Find the standing wave ratio, current standing wave ratio. So A, B, C, D, E, F. So where is the standing wave ratio? This is the answer of E and F. Because I told you current standing wave ratio and voltage standing wave ratio both are same. Actually the maximum value of current is I naught plus into mod of gamma L. And minimum value of current is I naught minus, sorry, I naught plus only. Here did I write down minus? Sorry. It is V naught plus only. Sorry. I naught plus 1 minus mod of gamma L. Okay, so this is the ratio. So answer is same for current standing wave ratio and current voltage standing wave ratio. Both are the same thing. But this formula that I have written, gamma L equals to ZL minus Z naught upon ZL plus Z naught. So this is the formula for voltage. This is the formula for voltage. The formula for current is just the negative. If someone asks you, this is very rare in the examination. But what if in 1 mark the question is coming? What is your reflection coefficient at load for current? What is your current reflection coefficient at load? This is very rare, but even if it comes, what you will find? The voltage reflection coefficient you will find, but the negative sign. Just I'm asking, just I'm writing down here. You don't need to mug it up. You don't need to watch it again and again. Voltage standing wave ratio. Sorry, not standing wave ratio. Sorry. Voltage reflection coefficient and current reflection coefficient are different. They have the negative sign. If voltage reflection coefficient is 0.5, then current reflection coefficient will be minus 0.5. But standing wave ratio for both of them are same. Because here what we are taking, here we are taking the magnitude. So minus 0.5, 0.5, both will have the same magnitude, no? So just I am asking you to remember this thing. Just keep it in mind. What if they ask the problem on current standing wave ratio? Very rare, but still if they ask. But we will solve all the problem if specifically if they are not asking about standing wave, sorry, reflection coefficient, then we will solve the problem of standing wave with respect to voltage reflection coefficient. So whatever that we are solving as of now, that is we are solving with respect to voltage, right? Next, what they are asking, on transmission line, what is the maximum value of resistance and where does it occur? So where does it occur? Maximum value of resistance, where does it occur? So at this point you are having voltage maxima and current minima. So where will be the maximum value of voltage will be, maximum value of resistance will be occurring? EF, G, EF, GH, G. R maximum occur at the same point of V max and I min. Now what is the value of R max? So there are two values on the whole transmission line. This is my transmission line. If I start working from y equals to 0 to y equals to L, I will get only two resistive element. What do I mean by that? That on the whole transmission line, what I will do, I will plot the gamma value, then I will make the gamma plane, then I will make this. First I will get the value of gamma, then I will make this particular circuit. Sorry, this particular circle. So let's just say this was my value of gamma. Here in this question, this is the value of gamma, no? This is how I am plotting the gamma, 63.43 degree. But it's not necessary that you will get this value only. It might happen you get value here, or here, or here, or here. So I am saying anywhere the value could be. Let's just say the value was here. I am starting my journey from this particular point. I am assuming it. So what will happen? I will walk on the complete circle. If I am walking on the complete circle, that means I am walking on the transmission line like this. So if I am walking on the circle, what is the value of impedance at this point? Capacitive complex. What is the value of impedance at this point? Capacitive complex. What is the value of impedance at this point? Inductive complex. What is the value of impedance at this point? Inductive complex. What is the value of impedance at this point? Inductive complex. What is the value of impedance at this point? Inductive complex. What is the value of at this point? Purely inductive. What is the value of impedance at this point? Purely capacitive. What is the value of impedance at this point? Resistive. Right? And what is the value of impedance at this point? Resistive. So on the whole transmission line, only two kind of resistance you can get. Are you getting this point? All these are inductive. Inductive element you will get infinity. Capacitive element you will get infinity. But resistive element, only two element you can get. One of them will be maximum, one of them will be minimum. What is this point? R minimum. And what is this point? R maximum. So this is the point of R maximum, this is the point of R minimum. So value of R minimum is defined as Z naught, R maximum is defined at Z naught. One will be multiplied with S, one will be divided by S. So let me know where I should multiply by S and where I should divide by S. Where I should multiply by S, where I should divide by S. So R minimum will be Z naught by S and R maximum will be S Z naught. Why is that so? Because S value will always be greater than 1. So for minimum value I need to divide it, for maximum value I need to multiply it. So R maximum occurs at the same point of V maximum and V minimum, and R minimum occurs at the same point of V minimum and I max. But you need to remember these values. What I feel is that this time the question will be framed from this particular portion. They will ask you the value of R minimum and R maximum on the transmission line. So first thing is that on transmission line, when you work on the transmission line, always maximum you can get two resistive element, R maximum and R minimum. That's it. Okay. What is the value of R minimum? Z naught by S. What is the value of Z naught? 50, right? What is the value of S? 2.62. And here 2.62 into 50. Whatever the value you get, 2.62 into 50. So 131 ohm. And 60 कर दिया गया यार, 2.62 into 50 करना था ना, 131. okay, 2.62. So this is 19. So when you work on the transmission line, the impedance, two resistive element you can get. One is 19, one is 131. Right? So this is actually not our y equals to 0. In this problem, this is our y equals to 0. So when I work for 0.088, after working for 0.088, I will get here and I will get this value, R max 131. And when I work for 0.088 plus lambda by 4, I will get this value, R minimum. Is that clear to you or not? Now next what they are asking. Yeah, sorry for the interruption. So next what they are asking, at what distance from load you will get purely inductive impedance and at what distance from load you will get purely capacitive impedance. So what you will think? By the scenario that I have taught, what you will think that, sir, I am starting my journey from here. Sir, this was my y equals to 0. This was my y equals to 0. So you have taught that, sir, I will always walk clockwise. And if I reach this point, this will be my purely capacitive. If I reach this point, this will be my purely inductive. This is what, sir, you have taught. So what that I have taught here, that your this point will be purely inductive and this point will be purely capacitive. That was actually wrong. This will not be always true. What I said, that upper part will be complex inductive, that is true. The lower part will be complex capacitive, that is also true. This part will be resistive. Basically, this part will be complex inductive, that is true. This part will be complex capacitive, that is also true. This part will be resistive, ZL greater than Z naught, that is also true. This part will also be resistive, ZL less than Z naught, that is also true. But here I said that the imaginary part, the imaginary axis will give purely inductive and purely capacitive. So I am really sorry for that mistake. That is not always true. This was true luckily in this case only. That was true only in this case, but it is not always true. So this is not certain. So I will remove this. You should also remove that concept from your mind. What you need to keep in mind, that sir, certainly upper part will be complex inductive, that is true. Lower part will be complex capacitive, that is also true. This is resistive, ZL greater than Z0, ZL less than Z0. All these are true. But what you said, that on imaginary axis, the real part, sorry, on imaginary axis, the positive part will be complex, the positive part will be purely inductive and negative part will be purely capacitive. That thing is wrong. Okay, that will not always be true. So now, what about this question? Now, what about this question, sir? So what about this question, sir? How we will solve it? That at what distance from load you will get purely inductive impedance and purely capacitive impedance? So I will just tell you one line, that unless your S is equals to infinity, that means unless your standing wave ratio is equals to infinity. For getting standing wave ratio equals to infinity, what do I need? That my mode of gamma L should be equals to 1. Because what is the formula? 1 plus mode of gamma L divided by 1 minus mode of gamma L. So if it is 1, then my standing wave ratio will be infinity. So either you can remember that unless my standing wave ratio is infinity or my mode of gamma L is equals to 1, unless these two conditions are there, I will never get purely inductive impedance on my transmission line. I will never get purely capacitive impedance on my transmission line. There is 0.00001% chance that they will ask this question in the examination. But even if they ask, okay, I randomly framed this option and I matched it up. To be very honest, I matched it up here. Here I should not even have said that where it is gone. At this point, I should not have said that this will be purely inductive and this will be purely capacitive. That is not the case. It will not always be true. Luckily, in this case, it was true, and I said that, and I matched up there. I am really sorry for this conceptual mistake, but you need to eradicate this thing from your mind. The point is, upper part will be complex inductive, lower part will be complex capacitive, resistive, ZL greater than Z0, ZL less than Z0. All these are true, and this middle point is ZL equals to Z0. All these are always true, but this thing is not always true. Luckily, in this case, it was true, but this is not always true. So then how will you solve these problems? So you just need to remember one thing, that if S is equals to infinity and mode of gamma L is equals to 1, unless this condition are occurring, in your transmission line, when you work on the transmission line, what I mean to say, when I work on this transmission line, from here I will start working. So when I work on the transmission line, I will never get purely inductive impedance, I will never get purely capacitive impedance. I will get purely resistive impedance for sure. Here I am getting. I will certainly get purely resistive impedance for sure. Where I will get? At this point and at this point. What is this point? This is the point of V maxima. So when I work for the distance of 0.088 lambda, so at that point I will get R maximum. That means my impedance will be purely resistive. And when I work for the distance of 0.388 lambda, at that point I will get R minimum. That will also be purely resistive, but I will never get purely inductive or purely capacitive. So those who are watching this concept for the first time, for them they can remember this line. But those who have studied Smith chart, they would be able to understand the reason as well. Why is that so? Because in Smith chart, where is our R equals to 0 circle? This is our R equals to 0 circle. In Smith chart, right? This is our R equals to 0 circle. And what is our mode of gamma equals to 1 circle? This is our mode of gamma equals to 1 circle only. So if my mode of gamma L equals to 1, then only my resistive part will be equals to 0, no? Let's just say if my mode of gamma L is equals to 0.5, then what will be my circle? This will be my circle. Now on this circle, this R equals to 0 circle will never cut. If my mode of gamma L is 0.5, this I am telling only for those students who are revising it. If you are studying it new, then you can skip this part. You can just remember this thing, that unless this is the condition, my purely inductive and purely capacitive load will never occur. Okay, or you can forget this part as well, because you don't need to remember all these things. But those who have already studied it, for them I am telling, those who have already studied the Smith chart, for them I am telling this thing. What I am telling, that if your mode of gamma is 0.5, then this will be your constant VSWR circle. And what is your R equals to 0 circle? This is your R equals to 0 circle. And this circle will never cut this circle. That means on this particular circle, on this gamma equals to 0.5 circle, your R can never be equals to 0. And if your R is never equals to 0, that means you will never get purely inductive part, you will never get purely capacitive part. Is that clear to you? So that was a big blunder from my side. At that point I said that this point will be the on imaginary axis, the positive part will be purely inductive and the negative part will be purely capacitive. When I said that point, that was pretty wrong from my side, and I am really sorry for that mistake. Okay, it should not have happened. That thing is not true at all. Okay, that was luckily we got in one case, and I thought that that is the case, but not. But that is not the case always. What is true is that upper part will be complex inductive, lower part will be complex capacitive. This part resistive, this part also resistive. ZL greater than Z naught, ZL less than Z naught, and middle part ZL equals to Z naught. That is true. Okay, let's go to the next question now. So this you will solve on your own. You will be able to do it. What I am asking, what will occur first? What do I mean by that? That first voltage minima will occur or current minima will occur. Then I am asking you the standing wave ratio as well. Then you can draw the standing wave pattern as well. Then you can tell me what will be the value of R max, what will be the value of R min, and where all these R max, R min will be occurring. All these points you can tell. Okay. And certainly here as well you can find one more point. What is that? What will be your standing wave ratio? Here also your standing wave ratio will not be equal to infinity. And if it is not equal to infinity, what does that mean? That your purely resistive and purely capacitive, purely resistive or purely inductive condition will never occur, right? Then we will solve these problems, and then we will solve this question. Okay, and after that we will make this table. So you can do everything on your own. Okay, these are just very simple concept. I hope you are enjoying the concept in a very good manner. So try doing it on your own. So let's start. I will start now. So what will be the value of reflection coefficient? You can calculate it on your own. So ZL minus Z naught, ZL minus Z naught upon ZL plus Z naught, ZL plus Z naught, right? ZL minus Z naught upon ZL plus Z naught. So we are getting 0.59 with an angle of minus 133.14 degree, right? So what is the first task? Always the first task is to draw it. Magnitude 0.59 and angle minus 133 point. Angle is greater than 90 degree, no? Angle is greater than minus 90 degree. So it will be like somewhere here. Basically, this is your minus 90. I am going clockwise, that means negative angle I am going. So this will be your 133.14 degree. Then what is the next task? The next task is to draw the circle. Circle taking this as radius. So taking this as radius, I have drawn the circle. Now I know one point where I will walk. How I will walk? Clockwise. I will walk clockwise. What will be this point? This will be the point of V minima. Left hand side, less priority, V minima. This will be the point of V maxima. So always I need to walk clockwise. So I will walk clockwise. So what will occur first? When I started walking from here, this is my y equals to 0. When I started walking from here, okay, walking, here I encounter voltage minima and current maxima and R minima. So what is occurring first? Voltage minima is occurring first. So what will occur first? Voltage minima will occur first, right? Or you can say current maxima will occur first. And at what distance from load your voltage minima will occur? At what distance from load voltage minima will occur? So what will be the answer? So I need to walk this much of angle. How much angle I need to walk? I need to walk this much of angle to reach to the voltage minima. So what is this angle? This angle is, let's just say this angle is theta. So here my theta is 180 degree minus 133.14 degree. 180 degree minus 133.14 degree. So this angle is 46.86 degree. So I need to walk for 46.86 degree to reach to my voltage minima. All good? So lambda by 2, or you can say 360 degree is equivalent to lambda by 2. So how much 46.86 degree will be equivalent to? So divided by 720, so 0.065. Okay, I forgot to multiply. No, 46.86, right? 46.86 divided by 720. Yeah. So 0.065. 0.065 lambda. I hope the calculation is correct only. Yeah. So this is the point of my first voltage minima. first voltage minima. Is that the only point where voltage minima will occur? No. If I talk about voltage minima, you can say voltage minima, or you can call it current maxima, or you can call it R minima. So first it is occurring at 0.065 lambda. Then next it will occur at 0.065 lambda plus lambda by 2. Next it will occur at 0.065 lambda plus lambda. In that manner it will keep on occurring. And what will be the location of voltage maxima? Or you can say current minima, or you can say R maxima. What will be the location? After this lambda by 4, right? At 0.065 lambda, what you are getting? Maxima. Sorry, at 0.065 lambda, you are getting voltage minima. So where you will get maxima? After lambda by 4 more distance. Basically, from from here to here, I will work for lambda by 4 more. If I work for lambda by 4 more, where I will reach? Here I will reach. So plus lambda by 4. Then next will be, so let's calculate it, plus 0.25. So this will be 0.315. 0.315. 0.315 lambda. So next will be 0.315 lambda plus 0.5 lambda. Next will be, in that manner it will keep on going. So this will be the location of V maxima, right? Now what will be the standing wave ratio? So first let's find the standing wave ratio. What is standing wave ratio? 1 plus mode of gamma L divided by 1 minus mode of gamma L. So 1 plus 0.59 divided by 1 minus 0.59. So 1.59 divided by 1.59 divided by 0.41. So 3.87. So if my standing wave ratio is not equal to infinity, this is not equal to infinity, what does that mean? That my minimum value will not be equal to 0. If standing wave ratio was infinity, what does that mean? Vmax divided by Vmin. That means minimum value will be 0. But that is not the case now. And now I am going to draw the standing wave pattern of voltage only. So first what we will get, voltage minima will get, but here there is nothing, neither maxima nor minima. But first we will get minima, 0.065 lambda. Then we will get maxima, minima, maxima. What will be the minimum value? What will be the maximum value? That I don't know. But I just know one thing, that first my minima is occurring. First my minima is occurring. That is at 0.065 lambda. Then after the distance of lambda by 4, after that distance of lambda by 4, maximum will occur. Then minima will occur, then maximum will occur. This is the standing wave pattern, right? Now, what is the value of Rmax and where I will get it? I will get Rmax here and R minimum here. What is the value of Rmax? S into Z naught. 3.87 into Z naught is 100 this time. That will be 387. And what will be the value of R min? Z naught by S. 100 divided by 3.87. So it is coming out to be 25.78 ohm. Okay, so these are the maximum and minimum value of resistances. But one conclusion you can see from here. What is that conclusion? Let's make the graph again. Okay, so in every question, what I'm gonna do? First, I'm gonna draw the circle only, right? First, I'm gonna draw the circle, taking that gamma L as radius. Now the thing is, where will be your y equals to 0? Let's just say my y equals to 0 is here, or my y equals to 0 is here. That means it is inductive part. It will be complex inductive. If my load is complex inductive, then I will be working somewhere on this part. This example I have already taken, so let's take the example of here. If my y equals to 0 is here, what does that mean? That means that my load is complex inductive. Now, where I will work? I will always work clockwise. So if I work clockwise, if I am working clockwise, so what I will reach first? What is this point? This point is V maxima. And what is this point? This point is V minima. So if I am working clockwise, what I am reaching first? Voltage maxima. So if my load is complex inductive, or it could be purely inductive as well. So if my load is inductive, then I will encounter voltage maxima first. And that you can see here as well. When your load was inductive, you encounter voltage maxima first. And current minima, you can say. And if your voltage is capacitive, sorry, if your load is capacitive, if my load is capacitive, I can be somewhere here as well. If my load is capacitive, so where I will start my journey from? Here I will start my journey from. So if my load is purely, if my load is complex capacitive or purely capacitive, then what I will start? I will start working in clockwise direction. So what I am encountering first? Voltage minima. So when your load is complex inductive, then first you will encounter voltage maxima, and when your load is complex capacitive, then first you will encounter voltage minima, right? And how you can remember it? What is the voltage for inductor? V equals to I into j omega L. So in case of inductor, who leads? In case of inductor, voltage lead, but in case of capacitor, voltage lag, because for capacitor this is the scene. So in case of capacitor, current is leading, and in case of inductor, voltage is leading. So when your load is complex inductive, then first your voltage maxima will occur or current minima will occur, and when your load is complex capacitive, then first your current maxima will occur or voltage minima will occur. Is that clear to you or not? In the examination, will you be able to answer this thing or not? Just you will draw the circle, you will take a random point, and then you will see first voltage maxima is occurring. There you go. And then first voltage minima is occurring. Will you be able to answer this thing? Is that point also clear? Why this is happening? That is also clear. Well and good. Okay. Right. So yeah, let's write down in a decent manner 0.065 lambda. Right. Okay. Let's go to the next one. Voltage, location of voltage maxima minima you need to find, standing wave ratio you need to find. So let's get started with the first one. ZL is equals to 50. So what will be your reflection coefficient? ZL minus Z0 upon ZL plus Z0. So that will be 1 by 3. What will be the standing wave ratio? 1 plus 1 by 3 divided by 1 minus 1 by 3. So standing wave ratio will be 2. So what do you see here? How will I draw the circle? So this is how I will draw the circle. The radius is 1 by 3. The radius, taking the reference of radius as 1 by 3, I will draw my circle. Sorry. From here 1 by 3, and then I have drawn the circle. So this will be the circle. Now what do you think where I am starting my journey from? Here I am starting my journey from. This is my y equals to 0. And what is this point? This is the point of R maxima only. Say yes or no. This is the point of R maxima or V maxima or current minima. I am starting my journey from here. This is my y equals to 0 point. I will start working clockwise. So at y equals to 0 itself, I am getting my voltage maxima. Basically, this is my transmission line. This is my transmission line. And my load is 100 ohm. My load is 100 ohm. My load is 100 ohm. So at y equals to 0 itself, I should get the value of R max. What is R max? R max, if you remember, R max is equals to S into Z0. What is the value of S? S is 2. What is the value of Z0? Z0 is 50. 100 ohms. So you are saying that your R max should be 100 ohm. And you are also saying that your R max should be occurring at 0, lambda by 2, lambda, and 3 lambda by 2, and so on. Let's check in the circuit if it is possible or not. Yes. When I see the transmission line at y equals to 0, I am getting 100 ohm. After lambda by 2, what I will get? 100 ohm. After lambda, what I will get? 100 ohm only. So is that point clear now? Why this formula came? Is that clear now? How this formula came? S into Z0. Now let's find the value of R minimum. R minimum. First, let me know where should R minimum occur. R minimum should occur where? So R minimum should occur after lambda by 4 distance, right? Because this is the point of R max, V max, and I min, and this is the point of R min, V min, and I max. So R min should occur after lambda by 4 distance. Say yes or no? Right? So after lambda by 4 distance, R min should occur. So from load after lambda by 4, R min should occur. So after lambda by 4, what should be the impedance? From load at lambda by 4 distance, what should be the impedance? If you remember yesterday's lecture, what did I say there? Z of phi will be Z0 square by ZL. That means 100 square, sorry, Z0 is 50. Z0 square by ZL. So because after lambda by 4, impedance are inverted. So Z0 square, 50 square by ZL. Right? So what will be the answer? 50 into 50 to 25 ohm. So you are saying that after lambda by 4 distance, I will get 25 ohm impedance. Now I'm not sure whether it will be R minimum or R maximum. I'm not sure. Okay, I'm sure as well, because after lambda by 4, I'm saying that my R minimum will occur, and that value is 25 ohm. Let's go by the formula. What is the formula that we have studied? Z naught by S. What is the value of Z naught? 50. What is the value of S? 2. What you are getting? R minimum equals to 25 ohm. Is that clear to you or not? Are you able to relate the things? This is equals to this one. This is equals to 100 ohm, this one. Are you able to relate the things or not? After lambda by 4, you are getting minima, R minima you are getting, or you can say I am getting voltage minima. Everything is being related now. Every single thing you can relate, all the dots you can relate, whatever that we studied yesterday, all the dots you are able to relate now. So what kind of standing wave pattern you will get? I am only drawing for voltage. Okay, I am drawing for voltage. So starting with maxima, then minima, and minimum value is not equals to 0 because standing wave ratio is not infinity. Okay, so this is how it will go. Starting with maxima, at 0 you are having maxima, then you are having minima, then you will have maxima and minima. So 0 lambda by 2, this is the point of voltage maxima, right? And what is this case? This case is ZL greater than Z naught. So when ZL is greater than Z naught and your load is purely resistive, then at the load itself you are getting voltage maxima. Now for the next case, what will be the scene? ZL less than Z naught. What I am talking about? I am talking about B. ZL is equals to 25 ohm, which is less than Z naught. ZL minus Z naught upon ZL plus Z naught, that is minus 1 by 3. So angle is 180 degree, right? Angle is 180 degree. Angle is 1 by 3 and angle 180 degree. So where I am starting my journey from? I am starting my journey from this point. What I will do? I will draw the circle. I am starting my journey from this point, y equals to 0. So I will go clockwise, right? I will go clockwise. This is the journey I am starting from. So here I will reach, what is this point? This is the point of R maxima, V maxima, I minimum. And what is this point? This is the point of V minima, I maxima and R minimum. Say yes or no? Right? Okay. So what is the scene here? This is your transmission line and your load is having 25 ohm resistance, right? And you are starting your journey from R minima only. That means at load you should get, here you should get what? V minima you should get, I maxima you should get, and R minimum you should get. So as per you, the value of R minimum is 25 ohm. But let's check according to our formula, what our formula says. So for applying the formula, I need to get the value of S. What is the value of S? S is 1 plus mod of gamma L divided by 1 minus mod of gamma L. So S is 2. The same circle I am getting. The value of S, 1 plus mod of gamma L. Here I am not going to put minus 1 by 3. I will put plus 1 by 3. S plus mod of gamma L. So what is the value I am getting? S is equals to 2. So what will be my R minimum? R minimum is Z naught by S. So what is the value of Z naught? 50 divided by S. R minimum you are getting 25 ohm. And that you should get at y equals to 0. Are you getting this thing? Yes. What about R maximum? R maximum is S into Z naught. S into Z naught. So what is the value of S? 2. What is the value of Z naught? 50. 100 ohm. And where you should get R maximum? R maximum you should get at y equals to lambda by 4, 3 lambda by 4 and so on. Right? So after lambda by 4 distance, after lambda by 4 distance from load, what will be the impedance you will get? Z naught square by ZL. That means 50 square divided by ZL. What you are getting? 100 ohm. Are you getting it? Yes. Are you getting 100 ohm? Yes, I am getting. Are you able to relate the things now? 100, 100. Say yes or no. So this is how things should be studied, right? Not by the formula. Theta, beta, 2, theta x, pi by 4, nah, nothing. Just a diagram and a soul. There you go. This is the pure concept here. And how these all concept came, why this became R maximum, why this became V maximum. So that we study in Smith chart actually. But even if you don't know this, still you will be able to solve the problem, right? Let's go to the third one. ZL is equals to 0. What is the value of gamma L? ZL minus Z0 upon ZL plus Z0. So gamma L is 1, minus 1 actually, 180 degree, right? This thing, and then from here we will start, then we will draw the circle, right? This is the point. We will draw the circle then. So where I am starting my journey from, here I am starting my journey from. This is my y equals to 0. So this is the point of voltage minima, right? Because already I know this is the point of voltage minima, this is the point of voltage maxima. So when I am having my short circuit load, at short circuit load, basically this is the condition that my load is shorted. My load is shorted. So let's go to the next page. My load is shorted. So here only I am having my minima, because impedance value is low, no? If ZL is less than Z0, so here you will have your minima, or you can say current maxima, or you can say R minima. Well and good. Where you will have your maxima? So location of minima are 0, lambda by 2, lambda, and so on. What will be the location of maxima? 0, sorry, not 0, lambda by 4, 3 lambda by 4, and so on. Say yes or no. Well and good. Everything is crystal clear, right? What we need, what else we can find? We can find the value of R min and R max. So R max should occur after lambda by 4 distance, right? After lambda by 4 distance, R max should occur. So here R max should occur. What will be the value of R max? If it is shorted, then at lambda by 4 it will be inverted, it will be open circuited. That means impedance should be infinity. So let's find the value of R max first. What will be my R max? R max should be S into Z0. Now what is the value of S here? Let's find the value of S. So 1 plus mode of gamma L divided by 1 minus mode of gamma L. So 1 plus 1 divided by 1 minus 1. So what is the answer? Infinity. What is the answer? Infinity. So S is infinity, Z0 is whatever it is. So what is the value of R max? That is infinity. Are we relating the things? This is infinity and this is also infinity. What should be the value of R minimum? That should be Z0 by S. What is the value of Z0? Whatever it is. S value is infinity. So R minimum is 0. R minimum is 0. And are we able to rate the thing? Yes. Here what is the value of your load? ZL is 0. And where we are expecting to be, where we are expecting it to be minimum, here we are expecting it to be minimum. Are you able to relate it now? Right? Now another thing. Here your S is equals to infinity. So now the thing comes. Which thing comes? What did I tell you? If your S is equals to infinity, or you can say mode of gamma L is 1, then you can have your inductive and capacitive load, purely inductive and purely capacitive load. So at this point, what is the scene? The resistance is infinity. And at this point, what is the scene? The resistance is 0. Now at this point, 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 you will always get purely inductive. Okay? Purely inductive. Although no one will ask you this thing, okay? Just for the information I am telling. And here you will always get purely capacitive. Look, you know that on the upper part, I will expect inductive load. It could be complex inductive. And at the lower part, I will expect capacitive load. It could be complex capacitive or purely capacitive. If your S is equals to infinity, then this load will be purely inductive and this load will be purely capacitive. And if your S is not equals to infinity, then never you will get purely inductive, never you will get purely capacitive. Now is that clear? If your S is equals to infinity, then always inductive, always purely capacitive. And if S is not equals to infinity, then never purely inductive, never purely capacitive. All good? So that real image, that real axis, that thing is not that imaginary axis positive part, imaginary axis negative part, that thing was not true. That was a blunder from my side. And that I eradicated in this video only. Well and good? Okay. So last part, ZL is equals to infinity. D. Point D is ZL equals to infinity. So can I leave it up to you? What will be the value of gamma L? Mode of gamma L. ZL is equals to, not mode of gamma L, sorry, mode of gamma L. ZL is equals to infinity. ZL minus Z0 upon ZL plus Z0. So if it is infinity, that means Z0 can be ignored. So it will be 1. Can I draw the circle? Yes, I can draw the circle. What will be the reflection of, what will be the standing wave ratio? 1 plus 1 minus 1. So that will be infinity. Yeah, here I forgot to draw the standing wave pattern. So for this particular circuit, what will be the standing wave pattern? So initially what I am having voltage minima. So I am drawing it only for voltage. So initially voltage minima. Now what will be the minimum value? What will be the minimum value? Since S is equals to infinity and that is equals to Vmax divided by Vmin. That means Vmin has to be 0. So minimum value will be 0 here. So this is how the pattern will go. Here your minimum value in these cases, ZL was 25 ohm. Here also you are getting minima, but S is equals to 2 here. Here your S is equals to 2. Here S is equals to 2. So if you draw the standing wave pattern for this particular circuit, so minimum value cannot be 0. You start from minima, but it will not be 0. So if I give you this particular standing wave pattern and then I ask you what will be the nature of load, what you will say? That's why it cannot be inductive. Why it is not inductive? Because in the inductive nature, in the inductive load, if it was inductive, let's see this example. If it was inductive, then at y equals to 0, we will neither get maxima nor get minima. If it was capacitive, then at y equals to 0, we will neither get maxima nor get minima. So it has to be resistive. Now the point will come whether it will be ZL greater than Z0 or ZL less than Z0. Then you will say that, sir, first what is occurring? First my voltage minima is occurring. This is the graph of voltage. So sir, first my voltage minima is occurring. That means it has to be ZL less than Z0. Then third you will say ZL will be equals to 0 or not. If ZL was 0, then my minimum value would have been equals to 0. When my ZL was 0, then my minimum value was 0. All these you don't need to mug up. This is there in your mind. Even if you forget anything, just draw the circle, everything will come onto you. That here you are having minima. These kind of questions we will solve as well. So no need to worry. So first I am starting with minima itself. If I am starting with minima itself, what is the value of minima? Minima is 0. That means my load will be certainly short circuited. Right? So this is how you need to think. So we will solve the problem. Do not worry. In the examination, just once you draw the circle, everything will come into your mind. And this is one of the complex topic which you are going to solve in a very easy manner. So no need to worry. Okay. So yeah, S is equals to infinity here. So first what will occur? First voltage maxima will occur. You can draw the circle as well. If I draw the circle, first my voltage maxima will occur. First voltage maxima will occur. So this is the condition. Here my voltage maxima will be occurring. Okay. Why is that so? Because where I am starting from? I am starting from here. I am starting from here because gamma value is 1 with the angle 0. So this is my starting point, y equals to 0. Here voltage maxima is occurring, then voltage minima will occur. And how much distance I need to walk? I need to walk for lambda by 4 distance to reach here. Right? I need to walk for lambda by 4 distance to reach here. So this will be the point of voltage minima. This is the point of voltage maxima already. So can you draw the standing wave pattern? Yes, I can draw the standing wave pattern as well. So how I can draw the standing wave pattern? So first what will occur? Voltage maxima will occur. Then voltage minima will occur. Right? So here voltage, this I am drawing for voltage. Then at lambda by 4, this will be 3 lambda by 4. This will be in between, this will be lambda by 2. And if someone asks you R maximum and R minimum, so you can directly say that, sir, here only I will get R maximum and that will be equals to infinity. And for R minimum will be equals to 0. And that I will be getting at lambda by 4 and 3 lambda by 4. Is that clear to you? All analysis is crystal clear. Let's see this option. Let's see this particular ZL equals to 100J. So what we will get? What will be the reflection coefficient? ZL minus Z0 upon ZL plus Z0. Right? J minus 1 upon 2j minus 1 upon 2j plus 1. Certainly the mode is 1 only, but what will be the angle? As far as I remember, it was 53.13 degree. So angle will be 53.13 degree. What is the next task? Next task is to draw the circle. Draw the circle taking what radius? Taking the radius as gamma L. Gamma L angle is 53.13. So this will be your 53.13. So this is your y equals to 0. So look here, y equals to 0. At y equals to 0, that means you are at load. At load, what impedance you are having? Purely inductive. So what did I say? Here only purely inductive will be. That is wrong. Here also you can get purely inductive. So you are having purely inductive load. What will be the value of what will be the value of S? Standing wave pattern. Sorry, standing wave ratio. So 1 plus mode of gamma L. What is the mode of gamma L? 1 only. Divided by 1 minus 1. So what you are getting? Infinity. So sir, here also my minimum value. What does that mean? That my V minimum and I minimum will be equals to 0. What does that also mean? That all this part will be purely inductive and all this part will be purely capacitive. Purely capacitive. Right? It will be purely inductive. So these are the conclusion we can make, and also we can make the minimum value will be 0. But what is the difference between this guy and this and this? What is the difference? The difference is here at y equals to 0 only you are getting either maxima or minima. But here at y equals to 0 you will not get neither maxima neither minima. At y equals to 0, that is the main difference. At y equals to 0, what you will get? So what do you think? At y equals to 0, are you getting maxima minima? No. What is the location of maxima? This is the location of maxima. So this is the location of V maxima. This is the location of V minima. So where will be my maxima occurring? So I need to work for the 53.13 degree. If I work for 53.13 degree, then I will get my voltage maxima. So lambda by 2, or you can say 360 degree is equivalent to, basically for V maxima, or you can say for R maxima, or you can say for I minima. How much I need to work? So 53.13 degree I need to work, which will be equivalent to, so 53.13 divided by 720 into lambda, which will be equivalent to 0.073 lambda. So I need to work for 0.073 lambda. That means at this point I will get my V maxima. Okay. And what about minima? What about minima? So for minima, 0.073 lambda plus 0.25 lambda. Then 0.073 lambda plus 0.75 lambda and so on. This will be the minima, this will be the maxima, right? What will be your R max? R max will be equals to, R max is Z naught by S, right? Z naught by, sorry, Z naught into S. So what is the value of S? Infinity. So R max is infinity. So maximum value of impedance is infinity. And what is your R min? R min is Z naught by S, that is equals to 0. Okay. So if someone asks you that at 0.073 lambda distance from load, what will be the value of what will be the value of impedance? At 0.073 lambda distance from the load, you will get R max, and that value is infinity. So in the formula that we have written, Z naught into ZL plus J Z naught tan beta L, tan beta Y. In place of Y, what you can put? 0.073. Then you can solve this thing and you will get to know that it is becoming equals to infinity. Okay. You can try solving this thing. You will get to know that at 0.073 lambda, if you put y equals to 0.073 lambda in this formula, you will get that your impedance is becoming infinity, right? And that is pretty obvious as well. By the diagram we can certainly tell. So I hope you are able to relate all these things, right? Let's solve for the second case as well. So for that I need to add a page. This is the blank page that I am having, which I can carry downward. Yeah. So let's solve for the second case as well. So ZL is equals to minus 100J. Okay, so what will be the reflection coefficient? ZL minus Z naught upon ZL plus Z naught. Z naught value is what? 50. Upon ZL plus Z naught. So minus 2j minus 1 divided by minus 2j plus 1. So certainly this is one angle will be just negative of this, no, minus 53.13. Are you sure about that? Let's check it. Minus minus 1 minus 2j here, and plus 1 and minus 2j here. And previously what was the scene? This was the scene, that plus 1 plus 2j and minus 1 plus 2j. So this angle we calculated, this angle now we are calculating. Yeah, angle will be just negative. Angle will be just negative, minus 53.13 degree. So this will be the value of gamma L, right? Can you calculate the standing wave ratio? Mode of gamma L is 1 only. So 1 plus 1 divided by 1 minus 1. Standing wave ratio is infinity. Okay. Yeah, here did I draw the standing wave pattern? No. So for the previous case, I forgot to draw the standing wave pattern. That is important actually. So what if I draw the standing wave pattern? How it will look like? I know that my minimum value will go to 0. My minimum value will go to 0. But at y equals to 0, I am neither having maxima nor I am having minimum. Maxima is occurring at 0.073 lambda. So I will start from here, then at 0.073 lambda maxima will occur, and then it will go like that. So when you see this kind of pattern, what you will understand, that minimum value is going to 0. Minimum value is going to 0. What does that mean? That s is equals to infinity. If s is equals to infinity, then s equals to infinity you can get in only 4 cases. What is that? If ZL is equal to infinity, ZL equals to 0, ZL is purely inductive, and ZL is purely capacitive. Now you need to think which of the following option is your final answer. So if ZL was infinity or ZL was 0, then at y equals to 0, you would be having either voltage maxima or voltage minima. But you are not having anything at y equals to 0. These options are gone. Now, at if your ZL was purely inductive, then first what will occur? Voltage maxima will occur. So yes, this is the answer. If ZL was purely capacitive, then what will occur first? Voltage minima would occur first. So that is not the answer. So this in this one, if I ask you what is the nature of load, what you will say? Sir, purely inductive. So in that manner, you need to think. They can give the standing wave pattern and then they can ask you what will be the nature of load. Okay, well and good. So s is equals to infinity, we are getting here s equals to infinity, we are getting, yeah. So let's draw the diagram first. Angle negative I need to take, and then I need to draw the circle. So first I am drawing the circle, but first you need to show this particular line. The angle is negative only. So now this is my y equals to 0. What I will do? I will start working. Where I will reach? I will reach at this point, which is my voltage minima, and then I will reach at this point. This is my voltage maxima, right? How much distance I will have to cover? This much angle I will have to cover. This is already 53.13 degree. So I need to work for this much angle. What will be this much angle? 90 minus 53.13. Minima. Minima angle is 90 minus 53.13 degree. Sorry. 180 minus. Really sorry. 180 degree minus 53.13. 53.3. So I need to work for 126.87 degree. So what will be this equivalent to? This will be equivalent to lambda by 720 into 126.87 degree. So divided by 720. This is 0.176 lambda. Okay, so that's the answer. So this is the location of voltage minima. Voltage minima you can say, current maxima you can say, and R minima you can say. What about voltage maxima? That will be occurring at 0.176 lambda plus lambda by 4. This is your lambda by 4 plus lambda by 4. 0.176 lambda plus 3 lambda by 4. In that manner it will keep on occurring. Say yes or no. Well and good. Okay. So you can draw the standing wave pattern. This was the case for, here only I am drawing. This was for ZL equals to 100J. Now I am drawing for ZL equals to minus 100J. This I am drawing for ZL equals to minus 100J. So what will happen? First voltage minima will occur. So I will start from here, voltage minima is occurring, then maxima in that manner. All good? So you must have understood all the points. Let's write down the summary. Now just the summary is there. If ZL is greater than Z0, if ZL is greater than Z0 and it is resistive load, so what do you think what will occur first? So in the examination you will not think that I remember this thing, that thing, nothing you are going to remember. First thing you can do is that you can take a random example. ZL is greater than Z0. You will take Z0 equals to 50 ohm, ZL equals to 100. You will find that the value of reflection coefficient is 1 by 3. So from where I will start the journey? Here I am starting my journey from. So what is this point? This point is Vmax. And what is this point? This point is Vmax. This point is Vmin. So I am already starting my journey from Vmax. So Vmax at y equals to 0. What will be the standing wave ratio? It will not be equals to infinity. Will not be equals to infinity. So standing wave ratio can be there from 1 to infinity, anything. Not equals to infinity. It will not be equals to infinity. It will neither be equals to 1, it will nor be equals to infinity. So will that be okay for you? Yes. If ZL less than Z0, then you will say, okay, ZL less than Z0, then here I will start my journey from. So Vmin at y equals to 0. What about standing wave ratio? It will be somewhere in between. What about if your load is R plus JXL? If your load is R plus JXL, that means somewhere you will be somewhere here. Let's just say I am somewhere here. R plus JXL. If your load is complex inductive, that means you are somewhere here. You will start your journey anti-clockwise. Sorry, clockwise. Really sorry. You will start your journey clockwise. So what will occur for? Vmax will occur first. Vmax occur first. Right? And what should be the standing wave ratio? It will also be somewhere in between. It cannot be equals to, like you can take the example as well, 50 plus 50J you can take, and then you will get to know that it will be also somewhere in between. If it is inductive, that means you will be somewhere here. So what will occur first? You can say that voltage minima will occur first. So V minima occurs first, somewhere between 1 to infinity. If it is purely inductive, then what will you understand? That angle could be anything. I can start my journey from anywhere. If it is purely inductive, here what did I do? You can take any example. You will get to know that you can start your journey from anywhere, but first V maximum will occur. V maximum occur first. But here the interesting point is your standing wave ratio is infinity. If Z is equals to minus JXC, then you can start your journey from anywhere. Did I draw the diagram for it? Yes. I can start my journey from anywhere, but I will be starting from the downward. From here I will be starting. So what will occur first? V minima will occur first. But the important point is, if it is equals to minus GXC, that means my mode of gamma L will be 1. My reflection coefficient will be equals to 1. Sorry, mode of reflection coefficient will be equals to 1. So my standing wave ratio will be equals to infinity. If ZL is equals to 0, standing wave ratio will be equals to infinity. If ZL is equals to infinity, standing wave ratio will also be equals to infinity. Right? But if ZL is equals to 0, that means ZL is less than Z0. So V minima at y equals to 0. And in this case, if ZL is equals to infinity, so V maxima at y equals to 0. What about ZL equals to Z0? No standing wave pattern. Why is that so? Because what will be the value of gamma L? For ZL equals to Z0, here I need to write down. Okay, let's remove it off. For ZL equals to Z0, what will be the value of gamma L? ZL minus Z0 upon ZL plus Z0. So gamma L will be equals to 0. So this is how the circle will look like. The circle is at origin itself, and there is no reflection. Gamma L is equals to 0. That means this is my forward traveling wave. There is no reflected back wave. There is nothing that is being reflected back. So there is no standing wave pattern. Or what is the standing wave ratio? Standing wave ratio will be equals to 1. Standing wave ratio will be equals to 1 because what is the definition? 1 plus mode of gamma L divided by 1 minus mode of gamma L. So standing wave ratio will be equals to 1. R max will be equals to R min only. Because what is the formula of R max? Formula of R max is S into Z0. And what is the formula of R min? Z0 by S. So if S value is 1, then R max will be equals to R min, and that will be equals to Z0 only. So everything is Z0. If your load is matched, then everywhere you will see Z0 only. Everything is Z0. Well and good. So this is the conclusion. There you go. And this is one of the finest problem of your GATE examination. This problem and this problem we will see, then this problem we will see, and then these questions we will see. So these are the questions of your gate examination that we are going to solve. Shall we solve it in this video or in some other video? Because it's been like this video is already of 2 hours. So let's start. In this video only we will solve. So voltage standing wave pattern is shown of a lossless transmission line with Z0 value is given, and voltage standing wave pattern is shown. Although I told you that standing wave pattern should be shown like this, but they are showing like this. It was given in the examination in this manner only. What do you see? At load, what is occurring? Voltage minima is occurring. At load, voltage minima is occurring. So what will be your first target? First target will be that, sir, I will draw the circle. Sir, forgetting everything, first I will draw the circle, sir. Because here I don't know the value of gamma L, but I know that my journey is starting from voltage minima. And where is my voltage minima? Voltage minima. So where my journey is starting from? My journey is starting from here. So this is my y equals to 0. So sir, from here my journey is starting from. So I am already at V minima. If I am at this point, so with respect to V minima, I am having R minima as well. And along with that, I am having my, what do we call it? I maxima as well. And one more thing I forgot to tell here, really sorry. If you attempted it on your own, then you might not be able to solve it now, because this value should have been given. This was 4, this was 1. 4 1 it was kya? Or it was 3 1. 4 minus 1 upon 4 plus 1. Yeah, it was 4 1 only. Okay, it was 4 1. So if from here I am starting, what does that mean? That my load has to be inductive only. Sorry, my load has to be resistive only. Because if it was purely inductive, or if it was anything, then you would have been starting from here, no? If it was complex inductive or purely inductive, you would be starting from here. If it was complex capacitive or purely capacitive, you would be starting from here. But if you are starting from this point, that means it has to be resistive only. So load is resistive. Resistive. What is the nature of load? Resistive. Resistive nature. And what is the value? So here what you will get? R minima you will get. At this point, what you are going to get? R minima. Right? And what is the value of R minima? Z0 by S. What is the value of Z0? 50. What is the value of S? What did I tell you? What is your S? V max divided by V min. That is 4 by 1. So value of S is 4. So what we are getting? 12.5. There you go. This is the answer. So your load impedance is, this is the load. What we are getting? Load impedance is, equals to 12.5 ohm. Did you understand the nature of load? And did you understand the value as well? Yes. Reflection coefficient. What about the reflection coefficient? Reflection coefficient. First, let me know what will be the angle of reflection coefficient. 180 degree. Because where I am starting my journey from? Here I am starting my journey from. That means my reflection coefficient would have been this. This would have been my reflection coefficient. And what is the angle of this reflection coefficient? 180 degree. Right? So what would have been my reflection coefficient? 180 degree. That means reflection coefficient would have been -1. So reflection coefficient is my -1. Right? So sorry. Really sorry. Blunder. यार मैं 2 घंटे से पढ़ा रहा हूँ ना, तो मेरा दिमाग थोड़ा सा सैचुरेट हो गया अभी. Really sorry. What will be the magnitude of reflection coefficient? That you don't even know, no? What will be the magnitude of reflection coefficient? That you don't know. What is the angle? 180 degree. So how will you find the magnitude of reflection coefficient? What is the formula you know? S is equals to 1 plus mode of gamma L divided by 1 minus mode of gamma L. This formula I already know, right? And if you adjust it, then mode of gamma L will come out to be S minus 1 upon S plus 1. You can try adjusting it on your own. Okay? Mode of gamma L will come out to be S minus 1 upon S plus 1. So 4 minus 1 upon 4 plus 1. So that will be 0.6. Angle you got to know, it will be 180 degree. Because this is how my reflection coefficient will look like. So angle is 180 degree. So angle is 180 degree, but magnitude is 0.6. So answer will be 0.6. Okay. Really sorry for that blunder. I need to take a break now because answer is minus 0.6 degree. Yeah. So that's the thing. Okay, we will solve, let's solve this question as well. The reflection coefficient of load is 0.2 angle with 30 degree. What will be the reflection coefficient at lambda by 8 distance away from load? Okay, so what they are saying, what did I tell you? This in this transmission line, what did I tell you? That whatever that you have found out, that is the reflection coefficient at load. You have find out the value, that is ZL minus Z naught. This is the reflection coefficient at load only, at load. When you walk along the transmission line, your reflection coefficient changes. And how it changes? So what I am going to do, at y equals to 0, what is my reflection coefficient? 0.2 30 degree, 0.2 30 degree. This is my y equals to 0. What I will do? Draw a circle, taking this as a radius. So this is my point of y equals to 0. Now how much I need to walk? I need to walk for lambda by 8 distance. This is the angle, this is the magnitude 0.2, angle 30 degree. How much I need to walk? I need to walk for lambda by 8 distance. What is lambda by 8 distance? And how I will walk? Always clockwise. I will walk clockwise. And what do you mean by lambda by 8 distance? Lambda by 2 is 360 degree, right? So lambda by 8 will be, lambda by 2 is 360 degree. That means lambda is equals to 180 degree. So lambda by 8 will be 180 degree by 8. क्या कर रहा हूँ यार मैं? Lambda by 2 is equals to 360 degree. So this will be 360 by 4. Very simple thing what I am doing. So this will be 90 degree basically. Very simple thing it is. So lambda by 8 should be 90 degree. So you need to walk for 90 degree from here. From this point I need to walk for 90 degree. So where I will reach? What do you think? From here in clockwise direction I need to walk for 90 degree. So where I will reach? Here I will reach, you know. I need to walk from this point, I need to walk for 90 degree. So this complete angle is 90 degree. This complete angle is 90 degree. That means how much angle I am making from x-axis? That is 60 degree, no? And it will be negative 60 degree. Are you able to understand this point? So what will be your reflection coefficient at y equals to lambda by 8? So your reflection coefficient at y equals to lambda by 8, what that would be? The magnitude will always remain same. The magnitude of reflection coefficient on the complete transmission line, the magnitude of reflection coefficient will be always 0.2. Just the angle will change. Now the angle has become minus 60 degree. Did you understand this point? What happened here? A very good question, very important question as well, and very important concept as well. That your reflection coefficient at load is 0.2 with the angle of 30 degree. You need to walk lambda by 8 distance away from the load. That means I am walking lambda by 8 distance away from the load. So where I have reached? I have reached here. Lambda by 8 distance means I need to walk for 90 degree. And I walked for 90 degree. That means I am at minus 60 degree now. So my reflection coefficient at y equals to lambda by 8. My reflection coefficient at y equals to lambda by 8 became 0.2 with the angle of minus 60 degree. So the magnitude of reflection coefficient on the complete transmission line remains always the same. Well and good. So this was a good question. Let's see this one. Try this on your own. So try this one on your own. And this is the best question of GATE examination. This was asked in GATE 2023. And you can go to the solution videos of GATE 2023. Just type GATE 2023 solutions by different coaching institute. They gave like, some take 25 minutes to solve it. Some did not even solve it. Okay. And some just gave the answer that this would be the answer. And now we will solve it on our own. You can also try it. I hope you will be able to do it. Think about it, what the user is doing here, what we are supposed to do, just think about it. Okay. And then we will solve this problem. Then here also I need to teach one concept. Okay. Here I will have to teach one concept, that the value of reflection coefficient is given. Then what is the ratio of reflected power to the incident power? This is just one formula that I am going to teach. So with that we will end the session. So first you try solving this question. Think about it. You have the ability to solve this question. The length is given of transmission line. Then find the total number of current minima on transmission line. This is what they are asking. So first you let me know where we will start from, what will be the condition. So yeah, just try solving it. Then I will come back and solve it. And we will proceed in the session. I am taking a break now. Okay, so did you solve this problem? What was the answer? I guess as far as I remember, the answer was 7. But yeah, let's get started. So what we need to do, we need to find the current minima. So first let's find the reflection coefficient. reflection coefficient at load, ZL minus Z naught upon ZL plus Z naught, that would be minus 1 by 3, right? So then what I will do, I will draw my circle. So where I am starting my journey from? I am starting my journey from y equals to 0. That means I am starting my journey from here. With this, I will make a circle now. I will make a circle. So this is the journey I am starting from. This is my y equals to 0. Then this is my y equals to 0. And what is this point? This point is your current maxima. Voltage minima you can say, or current maxima you can say. What do you need? You need current minima. So how much you need to walk? You need to walk and reach here. So at lambda by 4, what will be the location of current minima? Current minima will be occurring at lambda by 4, then lambda by 4 plus lambda by 2. That means 3 lambda by 4, then 5 lambda by 4. So these are the location of current minima. Just 1 second, I need to put that on. Yeah, so these are the location of current minimas. Now we need the value of lambda, right? We need the value of lambda. So what is the value of lambda? F I am having, and epsilon r is 4 here. So what I need, lambda is equals to Vp by F. And what will be Vp here? C upon under root epsilon r into F. So lambda will be equals to C is 3 into 10 to the power 8. What is your F? F is 3 into 10 to the power 7 divided by under root epsilon r. Under root epsilon r is 4. So 10 by 2, 5 centimeter, right? Lambda is 5 centimeter. So first minima is occurring at 1.25 centimeter. Second one will occur at 3 lambda by 4. So 1.25 plus 2.5. That means that will occur at 3.75 lambda, 3.75 centimeter. In that manner, it will keep on occurring. But we have a total length of 17 centimeter only. We have the total length of 17 centimeter. So this is what we need to find, that how many minimas will occur. 1, 2, in that manner you can count. Right? But I know that after every lambda by 2 it will occur. That means next, I don't know, like next where it will occur, 3.75 plus 3.75 plus 2.5. Basically 1.25. Then what is the value of lambda by 2 now? 2.5. So after every 2.5 centimeter, the minimas will keep on occurring. So 1.75, then 2.5, then another 2.5. What that would be? So that would be 5. So 6.25. Right? Then another minima will occur. I don't know where. Then next minima will occur at, I will add 5 here, 11.25. Then another minima will occur that I don't know at which location it will occur. You can calculate as well. How you will calculate? Plus 2.5. You just need to add 2.5 here. If I add 2.5, what I will get? 8.25 centimeter. Right? No, 2.5, 8.75. 8.75. 2.5. Then I need to add 2.5 again. So 11.25. Then I need to add 2.5 again. What I will get? 13.75. Then I need to add 2.5 again. So I will get 15.25. Right? Next, I need to add 2.5 again. So what I will get? 17.75. Right? So basically, am I doing the calculation correct? Here I added 2.5. What I'm gonna get? 14.75. Here I'm gonna get, no, 14.75. There is some calculation error by 1.25 plus 5. Okay, 3.75. 3.75 plus 5, 8.75. 8.75 plus 5, 13.75. Here plus 5, 11.25. Here plus 5, it will be 16.25. What this will be? Here it will be 16.25. Next, where it will be occurring? 18.75. So, but I have the length of 17 centimeter only. So this will not occur. So how many minimas are there? 1, 2, 3, 4, 5, 6, 7. So total minimas are total 7. So that's the answer. Okay. Total minimas are 7. Before going on to the next question, just to solve a revision problem. It is just like a revision problem. So what they are asking, find the reflection coefficient at lambda by 4 distance away from load. At lambda by 4 distance away from the load. This is what you need to find. So let me just tell me one thing. What is the reflection coefficient at load? That is ZL minus Z naught upon ZL plus Z naught. So that is equals to minus 1 by 3. So what I will do? This is what I will do. Minus 1 by 3. So this is the circle. I'm starting from here. This is my minus 1 by 3 because this will be the line I will be starting from here. This is my y equals to 0. How much I need to cover? I need to cover the distance of lambda by 4. Lambda by 4 is equivalent to what? Lambda by 4 is equivalent to what? 180 degree, right? So I need to reach here. Where I need to reach? Here I need to reach. So in this complete circle, the value of what is the scene that at reflection coefficient at y equals to lambda by 4. So magnitude will not change, only the angle will change. And how much is the angle now? If I have reached at this point, what is the angle? Angle has become 0 degree. So what is the answer? 1 by 3. So the answer is reflection coefficient at y equals to lambda by 4 is 1 by 3. Now there is another way of finding it out. What is that way? Let's just say I calculate the impedance here. What I am doing? I am calculating the impedance at lambda by 4. What that would be? What I am doing? Impedance at y equals to lambda by 4. This is a very important conclusion. What will be the impedance? Z0 square by ZL. Z0 square by ZL. What I am getting? 200. Right? Now, at this point, what is my impedance? Here, at this point, what is the impedance? 200. 200 ohm. Now, if I consider this point as load, then what will be my reflection coefficient? My reflection coefficient at lambda by 4. So what I'm going to apply? I'm going to apply the formula ZL minus Z0 upon ZL plus Z0. But now ZL I'm going to put 200. Basically, ZL minus Z0 upon ZL plus Z0. So what answer you will get? 1 by 3 only. So there are two ways. One way is that you can find the resistance at that point. What you can do? You can find the resistance at that point. If I find out the resistance at that point, you can consider that as a load. And then you can find the reflection coefficient. Or what you can do? You can find at the load, at the actual load, and then you walk away. But one thing is for sure, that on the complete transmission line, the value of reflection coefficient will be, the magnitude of reflection coefficient will be constant, only the phase will change. Here the phase was 180 degree. Here the phase was 180 degree. You will keep on walking this line, the phase will keep on changing. 180, 170, 160, 90. It will keep on changing. 0, then minus 90, minus 45, minus 90. In that manner, it will keep on going. But on the complete transmission line, the value will be 1 by 3 only. Is that okay for you or not? Right? Try this question. I am telling you, when this came, it was like one of the best question, and you can go and check the solutions. Even now in the textbook as well, in a lot of textbook, like a lot of calculation is involved. People think that this will be solved with a lot of calculation, but let's solve it without doing any calculation, just by the pure concept, whatever that we have studied, right? So what the user is doing here, a standing wave ratio of at standing wave ratio on 50 ohm lossless transmission line, that means Z0 is equals to 50 ohm. When it was terminated with ZL, then standing wave ratio was found to be 2. Now the distance between successive voltage minima is 30 centimeter. What does that mean? The distance between successive voltage minima is 30 centimeter. So that distance is lambda. So what is that distance is lambda by 2. So what is the value of lambda? 60 centimeter. And the first minima is located at 10 centimeter from load. So first what is occurring? Voltage minima is occurring or voltage maxima is occurring? You let me know. You let me know first voltage maxima is occurring or voltage minima is occurring. What they are saying? That first minima is occurring at 10 centimeter. They are giving the minima location at 10 centimeter. So if I say that, let's just say first voltage maxima is occurring. I am assuming that first voltage maxima is occurring. This is what I am assuming. So if first voltage maxima is occurring, then where will the voltage maxima occur? That what is the distance of minima minus lambda by 4? Say yes or no. If here you are having minima, then maxima will be lambda by 4 away. So I am assuming that first my voltage maxima is occurring. So if my first voltage maxima is occurring, then what would be the location of first voltage maxima? That would be the location of first minima minus lambda by 4. What is lambda by 4? Lambda by 4 will be 15 centimeter. So you are saying that your first maxima will occur at minus 5 centimeter. Is that possible? No. Is that possible? Not possible. What does that mean? That first your voltage minima will occur. They can give any value here. They did not say that first voltage minima is occurring. They are saying that anything can occur. Anything can occur. Like first maxima can occur, minima can occur. I am just giving the location of first voltage minima, that is 10 centimeter. If this was mentioned as 20 centimeter, if this was mentioned at 20 centimeter, then the scenes would have been different. First voltage maxima would have occurred if it was 20 centimeter, but it is 10 centimeter. If it was 20 centimeter, then you would have calculated this, it would have come 5 centimeter. So the graph would have been something like this, that first your maxima will occur, then minima, then maxima, then minima. But now what is the scene? Now if I draw the standing wave pattern, then this is how it will go. That first my minima will occur, and that in that manner. And what is this distance? This distance is 10 centimeter. Now can I draw the circle now? Can you draw the circle? Can you on the circle, can you let me know what will be there? We will read the question, but for this particular graph, can you draw the circle? Yes, you can draw the circle. This circle you have done. Now let me know where will be your y equals to 0. You understood that first your voltage minima is occurring. That means certainly you are somewhere here, but you will be here or you will be here. Think about it. What is the value of lambda? 30 centimeter, no, 60 centimeter. So what will be your lambda by 2? 30 centimeter. What will be your lambda by 4? That will be 15 centimeter. Right? What will be your lambda by 4? Lambda by 4 will be, did I calculate it correctly? Yeah, lambda by 4 will be 15 centimeter. Okay. Now what they are saying, you need to cover the distance of 10 centimeter to reach to the minima. This is my minima. This is my minima. I need to cover the distance of 10 centimeter. How much is this distance? How much is this distance? What is this complete distance? This complete distance is 30 centimeter, right? So how much is this distance? 7.5, right? Lambda, the distance between successive voltage minima, lambda by 2 was 30 centimeter only. So lambda was 60 centimeter. That means the complete distance is 30 centimeter. This complete distance, this complete circle is 30 centimeter. So how much will be this distance? 7.5. Say yes or no. And how much distance you need to travel to reach to the minima? To reach to the minima, you need to travel 10 centimeter. So that means certainly you need to be here, no? Are you getting this point? If you are here, then to reach to the minima, I will have to travel lesser distance. But I need to travel the distance of 10 centimeter. That means certainly my load would be somewhere here. So this would be my value. This would be my value. So I am at this particular point. Are you understanding this point? Right? Because you need to travel the distance of 10 centimeter. So this is another 2.5 centimeter. So here you are. This is your ZL. This is your ZL. Now what they are saying, and first minima, ZL can be replaced by an equivalent length LM and terminating resistance RM of the same line. What they are saying, ZL can be replaced with equivalent length LM and terminating resistance RM of the same line. What does that mean? That when you walk on this line, when I walk on this line, I will encounter two kind of resistance. What two kind of resistance? R maxima and R minima. So what you are doing, you are picking those resistance. You are picking those resistance and then you are extending your line by a LM length, and at the load you are using either R maxima or R minima. So when you use R maxima, then how much distance you need to walk such that you reach at ZL, and when you use R minima, then how much distance you need to walk such that you reach LM. Is that such that you reach ZL? Is that point clear to you or not? This is what they are asking. There is a transmission line, there is a load. So this is the condition of this transmission line. Now what you are doing, when you walk on the transmission line, you get two kind of resistance, R max and R min. What is the value of R max and R min? Can you calculate? Yes, I can calculate. Because what they have given, standing wave ratio they have given, no? They have given the standing wave ratio, that is 2. Right? So what will be the value of R max? R max will be S into Z naught, that is 2 into 50, that is 100 ohm. And what is R min? Z naught by S, 50 by 2, that will be 25 ohm. So what they are saying, if you walk on the transmission line, you will encounter two kind of resistances. Those are 100 ohm and 25 ohm. If I connect 100 ohm here, at the load, if I connect 100 ohm, then how much distance I need to walk such that my impedance here becomes ZL. And if I connect 50, if I connect 25 ohm here, then how much distance I need to walk such that the impedance become ZL here. So again, I will have to draw the circle again. Now this transmission line and this transmission line and this transmission line. Now you let me know both will have same kind of reflection coefficient or different reflection coefficient. What I am asking, this transmission line have a reflection coefficient, magnitude of reflection coefficient at load something. What is that you can find from here as well? That would be 1 by 3. This would be 1 by 3. So they are having the reflection coefficient at load that is equal to 1 by 3. Will they have the same reflection coefficient at load? This is my question. Yes. Why is that so? Because what you are doing, you are picking a resistance which is there in between the transmission line only, and then you are using that as a load. What I am saying, what if I would have walked for a particular distance and I would have got R max here? Okay, I would have walked for a particular distance and I would have got R max. I would have got R max, and if I have calculated the reflection coefficient here, what would be the magnitude of that reflection coefficient? That would be 1 by 3 only. Are you getting this point? Are you understanding this point? Are you understanding why I picked this question? Because what I am saying, on this transmission line, if I have walked for a particular distance, then after that distance I would have got R max. And at R max, if I have calculated the reflection coefficient, then the magnitude would have been same, angle could be something different, but the magnitude would have been same. And what formula I would have applied? The formula I would have applied is that R max minus Z naught upon R max plus Z naught. Say yes or no. If I apply this formula, if I had applied this formula, ZL minus Z naught upon ZL plus Z naught, I was getting the same answer. There are two methods, right? There are two methods of solving this problem. When I came back, I get 1 by 3. If I have worked on this transmission line, I would have got at R max. Then I would have got the reflection magnitude of reflection coefficient to be same that I was getting at load. And formula that I would have applied is R max minus Z naught upon R max plus Z naught. Now let me know what formula I will apply to get the reflection coefficient here. That would be R max minus Z naught upon R max plus Z naught. Is that formula same? This formula and this formula, is that formula same? Yes. That means magnitude of reflection coefficient will be same. So on a transmission line, if I walk on this particular transmission, what is the conclusion of this now? This is a very, very good question. What is the conclusion? That on this transmission line, if I walk, then whatever the impedance I get here, let's just say I am getting a random impedance that is ZA. This random impedance I am getting ZA. Now what do I do? I extend this transmission line. And at the load, I connect this ZA. At the load, I connect this ZA. And now if I ask you, what is the reflection coefficient here? So the same reflection coefficient will be the same that you are getting here as well. Why it is happening? Because of this analogy that I told you, that if you walk, then this is the answer you are getting. But what is the other way? The other way is, at this particular distance, at lambda by 4, you find the equivalent resistance. What is the equivalent resistance? Here at lambda by 4, the equivalent resistance was 200. So if you find the equivalent resistance and then you calculate the reflection coefficient considering that equivalent resistance as load, you will get the same answer. Here what we are doing, again I am explaining what we are doing. I am walking for a particular distance, so I am reaching at R max, and when I calculate the reflection coefficient at R max, I will apply the formula R max minus Z naught upon R max plus Z naught. So this will be my reflection coefficient at R max in this transmission line. Now what I am doing, I am extending this line and connecting R max or R min at the load. If I connect R max at the load, then what will be the formula I will apply? R max minus R naught upon R max plus R naught. So that means the reflection coefficient remains the same. For circuit 1 and for circuit 2, reflection coefficient remains the same. And what is the reason behind that? Magnitude of reflection coefficient remains the same. For circuit 1 and circuit 2, magnitude of reflection coefficient remains the same. Did you understand the reason behind that? Look, in whole YouTube you can find, you are not going to learn all these concepts. Okay, I am not only self-praising it, but these require a lot of concentration. So then only you understand these concepts. A lot of people have given the solution, but they did not even take this thing into action. They just said that reflection coefficient will be same. Why? What is the reason behind that? Why the reflection coefficient will be same? The magnitude of reflection coefficient will be same. So what does that mean? That now this circle will be taken for the other transmission line as well. This we are drawing for transmission line 1. this circle I have drawn for transmission line 1. If this magnitude was changing, if the value of mode of gamma was changing, then the radius of circle would change, no? Because what do? First I plot my mode of gamma, then with that radius I draw the circle. But now my mode of gamma is the same. What is my mode of gamma L? My mode of gamma L is 1 by 3. If Rm is connected to Rmax, so what will happen now? What will happen is that where I will start my journey from? I will start my journey from, where will be Rmax? Here will be Rmax. I will start my journey from here. Where will be Rmin? Here will be Rmin, but I don't care. So now in the next graph, in the transmission line 2, this is the curve I will get. And for that, what will be the reflection coefficient at load? Since I am using Rmax, so this will be the reflection coefficient at load. Because I am using Rmax, so I will be starting with maxima. Now where do I need to go? I need to walk. I need to walk in clockwise direction, and I need to walk such that I reach this point. And where is my ZL? This is my ZL. I need to walk, and I need to walk such that I reach ZL. Here will be my ZL. So what is this distance? This distance is 2.5 centimeter, right? And what is the total distance? This total distance. What is this total distance? The total distance is 7.5 centimeter. That means I am here. When I started analyzing this transmission line, I started from here. Now this is my y equals to 0. For me, this is my y equals to 0. Now I will walk on this transmission line. Then how much distance I need to cover such that I reach to ZL? I need to cover 7.5 minus 2.5. That means I need to cover 5 centimeter distance. So that means if you have connected 100 ohm resistance at the load, then you need to cover 5 centimeter distance to reach this point. Understood? Okay. So this was the first part. Now second part. What will be the second part? The second part will be if my Rm is equals to Rmin. So there is no doubt that the reflection coefficient will be the same only. That means the circle will be the same. Circle will be the same means the radius of the circle will also be the same. Everything will be ditto same. The radius will also be same. The circle is exactly the same. I know on this circle I will be having ZL here. But where I will be starting my journey from? I will be starting my journey from R minimum, because I have connected R minimum. What does that mean? That if I have connected R minimum, so this is what it means. This is what it means that I have connected R minimum. Okay. And you know this is 7. And now where I will walk? I will start walking. This is my y equals to 0. Now I will start walking, and how I need to walk? I need to walk clockwise. And here I will reach. So how much distance I will have to cover? 7.5 plus 7.5, and what is this distance? 5 centimeter. And what was this total distance? 15 centimeter. So if Rm was equals to R minimum, and what was the value of R minimum? 25 ohm, right? R minimum was 25 ohm. Then you need to walk for 20 centimeter. And if Rm was equals to R max, and that was equals to 100 ohm, then you need to work for 20 centimeter. Yeah, then you need to work for 5 centimeter. So this is the answer. A great question and a great way to solve it. Important point was why the circle are same. Even if you don't think in the examination that sir why circle are same, so like the worst possible case, what would have occurred to you? That you are using a resistive element. That means you will start your journey from here. So R minimum could be there, R maximum could be there. You will find the value of R minimum, R maximum, then you will say what is this distance, then what is this distance. You would be able to do the answer in the examination. But as an educator, it's my duty to tell that why the circle did not change. Because if I change the load, then gamma value should change, no? Because reflection coefficient is ZL minus Z naught upon ZL plus Z naught. So if ZL is changing, then gamma value should change. But this ZL you are getting from the transmission line itself. This ZL Rm of the same line That means if you work on the line, then whatever the RM you get, only two kind of RM you will get. Those RM you are using here. So if you are using the resistance of the same line, then your magnitude of reflection coefficient will not change no matter whatever the length of transmission line is there. Very interesting point. Like the educators, the professor of IITs thought of it. They have been teaching the transmission line for a very long time, so they thought of it. Then they framed the question. But we, as an educator of GATE, we failed to see the beauty of this question. We just solved it applying the equation and all those things, but they expected this answer that someone will solve in this manner, right? So I hope now that point is clear, that what all are the beauty behind all these things and why I took this session. That was also very important. Well and good. Now the next question, this is just a formula based. Now these kind of simple question can also be asked. So what they are asking, so there will be some incident power, no, right? And then there will be some reflected power. There will be load, right? Load in the transmission line. Just formula I will tell, because who knows, this may be asked. So some power will be incident, some power will be reflected back, and some power will be transmitted. So reflected power is 1 minus mode of gamma square of incident power, and transmitted power is gamma square of incident power. Okay, will you be able to remember? This is easy to remember, right? And then you can remember that incident power will be equals to reflected power plus transmitted power. So what they are asking, find the ratio of reflected power to the incident power. Since it is power, so it will be 1 minus mode of gamma square. So that will be 1 minus 0.5 square. 0.25, that would be 0.75. That's the answer. Okay. So these kind of questions they can ask in the examination. So this was just a formula based question that I wanted to teach, and rest all the things have been studied, and now you are much clear that what I feel is that if they want to frame a good question and like this will be there, if they think about EMFD, then this will be the first topic that they will think about to frame the question. This is what I feel. Okay, so you can be confident now, even if you haven't studied EMFT. Now you have spent roughly around 3 to 4 hours on EMFT and you are confident enough, like you will be much confident than any guy who would have studied from anywhere. Believe me. Okay, you will be much confident in EMFT, at least in these topics. Well and good. Okay then, thank you very much. And do comment down how did you find this video.